It's a question that seems simple at first. What is nothing? Yet it has been a riddle that has baffled thinkers for centuries. Is it simply an empty void, a blank space where nothing exists, or is it something more profound, more elusive? Philosophers, scientists, and artists have all sought to understand this enigma from different perspectives, each offering their own interpretation of the idea of nothing. For some, it is an abstract concept, an absence that can't truly be grasped, while for others, it may hold the key to understanding the very nature of existence itself. What then is this nothing we speak of? Let's embark on a journey to explore this profound mystery. The universe, in all its vastness, forms the grand stage of existence, a boundless expanse that stretches across the very fabric of space and time. This sprawling cosmos is the arena in which galaxies, stars, and planets play out their cosmic drama. Scientists estimate that the observable universe spans a mind-boggling 93 billion light-years in diameter. This figure, though already astounding, may be just the beginning. New discoveries suggest that the actual size of the universe could extend far beyond what we can currently see. But what does this immense scale mean in practical terms? The universe is also ancient, around 13.8 billion years old. Within this vast expanse, there are roughly 2 trillion galaxies, each one teeming with millions, if not billions, of stars. Our own Milky Way galaxy, for instance, contains around 100 billion stars. These galaxies don't exist in isolation. They form a cosmic web, bound together by invisible forces and interwoven with the mysterious substances of dark matter and dark energy. Though scientists have yet to directly observe dark matter and dark energy, they are believed to account for about 85% of the total mass of the universe. They play a crucial role in the universe's structure and influence its continuous expansion. Yet, the universe isn't simply a vast collection of celestial bodies. It is far more intricate than that. It is a constantly evolving entity, shaped by the laws of physics. From the tiniest subatomic particles to the largest galaxies, the cosmos operates according to an elaborate set of rules. The Big Bang Theory offers a compelling explanation for the origins of the universe, suggesting that it began as a singularity, an infinitely dense point, and has been expanding ever since. This model helps to explain not only the distribution of galaxies across the universe, but also the cosmic background radiation that permeates the cosmos. As we look deeper into the universe with increasingly sophisticated instruments, we continue to uncover more and more complexities that were once hidden from view. Telescopes such as the Hubble Space Telescope and the more recently launched James Webb Space Telescope have allowed us to peer into the farthest reaches of space, capturing light that has traveled billions of years to reach us. With each new discovery, our understanding of the universe becomes richer, though we remain keenly aware that there is still so much more to learn. The true nature of the universe, its vastness, and the laws that govern it continue to deepen our sense of awe. But even as we peer deeper into the cosmos, the scale of the universe remains utterly incomprehensible. To offer a sense of its enormity, the observable universe at 93 billion light-years in diameter is so vast that light, traveling at the staggering speed of 186,000 miles per second, would take 93 billion years to travel from one end to the other. This vast expanse hosts an unfathomable number of galaxies, each containing billions of stars and potentially even more planets. And yet, this observable universe, what we can see with our most advanced instruments, is not the true edge of the cosmos. It simply marks the furthest distance light has had time to travel since the Big Bang. Beyond this limit, there may be more of the universe that remains hidden, still beyond our reach. This realization that the observable universe might only represent a fraction of the total cosmos forces us to confront a humbling thought. Our Earth, with all its wonder and complexity, is but a speck in the vastness of the universe. The observable universe, the portion that we can study with the help of modern technology, is not confined by any physical barrier. Instead, it is limited by the speed of light and the age of the universe. With the universe being approximately 13.8 billion years old, the farthest distance that light could have traveled to reach us is also around 13.8 billion light years. However, due to the ongoing expansion of the universe, the actual distance to the edge of the observable universe is closer to 46 billion light years in every direction. This brings the total diameter of the observable universe to about 93 billion light-years. This immense size, while overwhelming, is only one aspect of the cosmos. The observable universe is a treasure trove of astronomical phenomena: sparkling galaxies, enigmatic black holes, star clusters, and glowing nebula. These phenomena offer invaluable insights into the nature of the universe, from its beginnings to its current structure and ongoing evolution. The deeper we peer into the cosmos, the more we realize how much there is yet to discover. But the universe, as vast and mysterious as it may seem, may still be only a fraction of a far larger reality. Some cosmological models propose that the universe could be infinite, extending far beyond the limits of the observable realm. It's an idea that pushes the boundaries of human understanding. As we continue to refine our technologies, such as the Hubble and James Webb Space Telescopes, we can probe the furthest reaches of the universe, capturing light from objects that are billions of years old. While these instruments are bound by the limits of light and time, they have granted us unprecedented glimpses into the history, structure, and potential future of the cosmos. Measuring the size of the universe is a monumental task that blends cutting-edge technology with sophisticated scientific theory. At the heart of this measurement is the speed of light, which acts as our cosmic ruler. Light travels at roughly 186,000 miles per second, and by studying light from distant galaxies, we can determine how far it has traveled, offering a way to measure distances across the cosmos. One of the key tools used in these measurements is the phenomenon known as redshift. When light from distant galaxies shifts toward the red end of the spectrum, it indicates that the universe is expanding. The greater the redshift, the further away the galaxy is, and by studying this relationship, known as Hubble's law, scientists can calculate the distances to galaxies that lie billions of light years away. Advanced instruments like the Hubble and James Webb Space Telescopes have revolutionized our ability to measure these vast distances with incredible accuracy. As we continue to explore the universe's depths, each new discovery offers us another piece of the cosmic puzzle, revealing ever more about the scale, structure, and evolution of the universe. Yet, despite our impressive strides, we are only scratching the surface of understanding what the universe truly is. Observing distant stellar explosions with known intrinsic brightness has long served as one of the most reliable ways to measure the vast expanses of space. These cosmic events, particularly supernovae, function as standard candles, offering astronomers the ability to measure distances across the universe with remarkable precision. In addition to this method, another pivotal tool in understanding the universe's vastness comes from the cosmic microwave background radiation, the afterglow of the Big Bang. This faint radiation provides a snapshot of the universe's infancy, offering insights into its early conditions and aiding in the refinement of estimates regarding its size and age. Through these techniques, scientists have determined that the observable universe spans an astonishing 93 billion light-years in diameter. Yet, the true extent of the universe remains one of the most profound and captivating questions. Does it extend beyond what we can see, perhaps infinitely? Or is it merely a portion of a far grander structure, possibly a multiverse? These remain open questions that fuel both scientific inquiry and philosophical reflection. At its most fundamental level, the universe is an intricately woven tapestry, composed of countless galaxies, stars, planets, gas, dust, and mysterious substances such as dark matter. These elements are held together by gravity, the force that governs the cosmic dance of all matter. The observable universe alone contains an estimated 2 trillion galaxies, each with its own unique structure and characteristics. These range from tiny, faint dwarf galaxies to massive, sprawling giants. Our home galaxy, the Milky Way, is a spiral galaxy with over 100 billion stars. Stars, the luminous engines of the universe, shine brightly by undergoing nuclear fusion in their cores, a process that produces light and heat. These stars vary widely in size and color, from the faint red dwarfs to the massive blue giants and supergiants. The life cycle of stars is dramatic, and some end in spectacular explosions known as supernovae. These cataclysmic events can give birth to neutron stars or black holes, objects so dense that they warp the very fabric of space-time itself. The remnants of these explosions also serve another crucial function. They enrich the surrounding space with heavier elements, providing the building blocks for new stars, planets, and even life itself. Planets, which often orbit stars in complex systems, come in a wide range of types and sizes. These include rocky terrestrial planets like Earth and Mars, as well as gas giants like Jupiter and Saturn. Beyond our solar system, countless exoplanets orbit other stars, expanding the number of worlds beyond our imagination. Smaller celestial bodies, such as moons, asteroids, and comets, further complicate and enrich the dynamic nature of these stellar systems. Between and within galaxies lies the vastness of interstellar and intergalactic space, a realm filled with gas, dust, and the raw materials necessary for the formation of new stars. But space is not empty. A mysterious substance known as dark matter permeates the universe, though it remains invisible to direct detection. Dark matter can only be observed indirectly through its gravitational effects, yet it accounts for about 85% of the total mass of the universe. Equally enigmatic is dark energy, a force that is thought to be driving the accelerated expansion of the universe. Dark energy constitutes roughly 68% of the universe's total energy content, though its true nature remains a subject of intense research and speculation. Together, dark matter and dark energy form the vast, invisible majority of the universe, creating a cosmic landscape of extraordinary complexity. The universe, with all its stars, planets, galaxies, and strange substances, presents a vast and intricate field of exploration, constantly expanding our understanding and challenging the boundaries of what we know. Each discovery opens new avenues for inquiry, fueling humanity's unrelenting curiosity about the cosmos. The concept of nothing, especially in the context of the universe's origin, presents an even more profound challenge to our understanding. In everyday language, nothing might suggest an absence of everything, no matter, no energy, no space, and no time. But when applied to cosmology, the idea becomes more elusive and multifaceted. Before the Big Bang, which occurred approximately 13.8 billion years ago, there was no space or time as we understand it. In fact, there wasn't even an empty void. The very fabric of space-time did not exist. One way scientists attempt to conceptualize this state of nothing is through quantum mechanics and the vacuum state. According to quantum theory, even what we consider to be a perfect vacuum is not truly empty. Instead, it is filled with temporary particle-antiparticle pairs that pop in and out of existence, a phenomenon known as quantum fluctuations. In this context, nothing doesn't mean an absence of potential. It means a state where classical matter and energy are absent, but where quantum fields still give rise to fluctuations that could, in theory, lead to the creation of particles or even entire universes. Other cosmological models, based on the principles of general relativity, suggest that space-time itself is shaped by the presence of mass and energy. In the absence of both, space-time, as we understand it, ceases to exist. Thus, in this view, nothing could mean a state in which neither space nor time has any meaning or definition. The transition from this profound nothingness to the birth of the universe remains one of the most pressing and profound mysteries in science. While nothing, in the cosmological sense, is not a void, it is instead a state that precedes the creation of space, time, and matter. How the universe emerged from this nothingness remains one of the most captivating questions in both science and philosophy. The origin of the universe is a question that has captivated the curiosity of humanity for millennia. It transcends mere academic inquiry, forming the very foundation of our understanding of existence. Unraveling the mysteries of the universe's birth is more than just a scientific pursuit. It is the cornerstone of our quest to comprehend the fundamental nature of reality itself. By studying the origins of the universe, we not only explore the beginnings of space, time, and matter, but also gain insights into the fundamental forces that govern the cosmos, including gravity, electromagnetism, and the nuclear forces. In this way, the exploration of the universe's origins holds the potential to unlock secrets that link the macroscopic scale of galaxies with the microscopic realms of quantum mechanics, deepening our understanding of the fundamental laws that shape our reality. It is a journey of discovery that promises to reshape our conception of existence itself, pushing the boundaries of what we know, and encouraging us to look beyond the stars for answers to the most profound questions of all. Moreover, contemplating the universe's inception triggers profound existential reflections that tap into our innate desire to understand our place within the vast expanse of existence. Scientific theories exploring the origins of the cosmos, ranging from the Big Bang to the theory of cosmic inflation, challenge and expand our perceptions, urging us to rethink time, space, and existence itself. These theories push us to reconsider the very fabric of reality and spark continuous advancements in technology and scientific exploration. The quest to uncover the secrets of the early universe propels innovation across disciplines, from astronomy to particle physics, leading to the development of sophisticated tools like cutting-edge telescopes and particle accelerators. Therefore, the pursuit of understanding the universe's beginnings is not only a matter of tracing the cosmic timeline, but also a journey to expand the boundaries of human knowledge and inspire breakthroughs that could shape our future. Long before the advent of modern science, ancient civilizations crafted intricate, imaginative narratives to explain the universe's creation. These creation myths, rich with symbolism, provided a framework not only for understanding the cosmos, but also for embedding cultural, spiritual, and moral significance into the universe itself. In ancient Mesopotamia, for example, the Babylonian creation epic, the Enuma Elish, recounts the story of how the god Marduk vanquished the primordial sea goddess Tiamat and used her body to form the heavens and the earth. This myth intertwines the origin of the cosmos with the triumph of order over chaos, a theme that resonates throughout various creation stories. Similarly, in ancient Egypt, the mythologies surrounding the god Atum are foundational. Atum, emerging from the chaotic waters of Nun, was believed to have created himself before giving birth to the gods Shu and Tefnut. These gods, in turn, created the earth, Geb, and the sky, and Nut, establishing the basic components of the universe. Through these stories, ancient Egyptians were not only given a model of cosmic origin, but also a vision of continuity and divine order in their daily lives, reinforcing the interconnectedness of all things. The ancient Greeks also contributed greatly to cosmological thought, with Hesiod's Theogony providing one of the most influential accounts of creation. According to Hesiod, the universe began with chaos, a void or nothingness, from which the primordial deities Gaia, Earth, Tartarus, the underworld, and Eros, desire, emerged. These entities gave rise to the gods and, ultimately, the physical world. The Greek myths often focused on the role of the gods in shaping both the universe and human destiny, reflecting broader Greek views on power, morality, and the natural order. In Hindu cosmology, the Rig Veda describes a universe that emerged from a cosmic egg, Hiranyagarbha, and followed cycles of creation, preservation, and destruction. The deities Brahma, Vishnu, and Shiva are central to these cycles, representing creation, maintenance, and dissolution, respectively. This eternal process of cosmic regeneration, known as yugas, illustrates a universe in constant flux, governed by divine will and universal laws. These beliefs underscored the interconnectedness of all existence, with creation being both cyclical and ever-evolving. Despite the differences in their specific narratives, these myths all shared a common objective: to elucidate the mysteries of the universe and humanity's place within it. They provided not only cosmological insights, but also ethical guidelines, social structures, and a sense of purpose, grounding the people in a larger narrative. These creation stories served as vehicles for cultural identity and continuity, passed down through generations, each one a reflection of the values and worldview of its society. The ancient Norse also contributed their own dramatic creation myth. According to the Prose Edda, the universe began with a vast void known as Ginnungagap, flanked by two realms, Niflheim, a land of ice and mist, and Muspelheim, a realm of fire. When the ice and fire met, they gave birth to the giant Ymir and the primordial cow, Audhumla. Ymir's body was then used by the gods Odin, Vili, and Ve to create the world. His flesh became the earth, his blood the oceans, his bones the mountains, his skull the sky, and his eyebrows the barrier between the gods' realm and that of humans. This story not only explains the origin of the physical world, but also symbolizes the cyclical nature of creation and destruction, with the gods emerging from the chaos to impose order. Chinese mythology offers another fascinating perspective with the myth of Pangu, the giant who emerged from a cosmic egg containing the forces of yin and yang. By separating these opposing forces, Pangu shaped the earth and the sky. As he grew, he pushed the sky upwards and the earth downward, creating the physical world. After his death, his body transformed into various natural elements. His breath became the wind, his voice thunder, his eyes the sun and moon, his body the mountains, and his blood the rivers. Pangu's story highlights the balance of opposing forces and the interconnectedness of all things in nature. In the mythology of the Maori people of New Zealand, the universe's creation is linked to the separation of the Sky Father, Rangi, and the Earth Mother, Papa. Initially locked in a tight embrace, their separation was initiated by their children, the gods, who sought light and space in the world. After multiple failed attempts, the god Tane Mahuta succeeded in prying them apart, allowing the sky to rise above and the earth to settle below. This separation brought the world into being, creating the space for life to flourish. This myth encapsulates the struggle for balance and light, themes that resonate with many cultures' creation stories. These diverse creation myths, while differing greatly in their details and characters, often share similar themes: the struggle between order and chaos, the transformation of primordial entities into the physical world, and the active involvement of divine beings in shaping the cosmos. They reflect humanity's universal quest to make sense of existence and understand the forces that govern the universe. As human understanding evolved, early philosophers and scientists began to transition from mythological explanations to more rational, observational approaches. Ancient Greek thinkers like Thales of Miletus were among the first to attempt to explain the natural world using reason. Thales proposed that water was the fundamental substance of the universe, from which all matter originated. His pupil, Anaximander, suggested a more abstract concept, a peiron, an infinite and indefinite substance from which all things emerge and to which they return. Heraclitus, another Greek philosopher, introduced the idea that change is central to the universe, famously stating that you cannot step into the same river twice. Plato, in his work Timaeus, envisioned the cosmos as a creation of a divine craftsman, or demiurge, who imposed order upon chaotic pre-existing matter. Plato's model suggested a geocentric universe, with Earth at the center, surrounded by perfect circular motions of celestial bodies. Aristotle, Plato's student, further developed this geocentric model. In his work On the Heavens, he argued that the universe was finite and spherical, with Earth at its center, surrounded by concentric celestial spheres. The heavens, for Aristotle, were unchanging and made of a special substance called ether, distinct from the corruptible matter found on Earth. During the Hellenistic period, philosophers like Claudius Ptolemy and Epicurus made further contributions to cosmology. Ptolemy's Almagest became the definitive astronomical guide for centuries, refining the geocentric model and predicting planetary movements with remarkable accuracy. Epicurus, however, proposed an atomistic view of the universe, influenced by Democritus, suggesting that the cosmos was composed of indivisible particles and voids, functioning without the need for divine intervention. In the Islamic Golden Age, scholars like Al-Hazan, Ibn al-Haytham, and al-Biruni made significant strides in observational astronomy and experimental science, refining the existing models and laying the groundwork for future scientific developments. Al-Hazan's work on optics and his method of systematic experimentation influenced later scientific methods and helped shift the emphasis from purely philosophical speculation to empirical inquiry. The Renaissance and the subsequent scientific revolution marked a pivotal turning point in our understanding of the universe. Nicholas Copernicus proposed a heliocentric model, placing the sun at the center of the universe rather than the Earth. This revolutionary idea was later supported by astronomers like Galileo Galilei and Johannes Kepler, who refined Copernicus's model and laid the foundation for Isaac Newton's laws of motion and universal gravitation. These paradigm shifts not only redefined our conception of the cosmos, but also marked the evolution of science from philosophical speculation to empirical inquiry. Thus, early philosophers and scientists viewed the universe through a complex interplay of observation, speculation, and evolving methodologies. Their ideas laid the foundation for the profound advancements that would come in the modern scientific era. reshaping our understanding of the universe and our place within it. In the history of cosmology, one of the most influential theories to emerge from ancient thought was the geocentric model, famously articulated by the Greek philosopher Aristotle in the 4th century BCE. Aristotle's vision of the cosmos was profoundly centered on Earth, which he placed at the heart of the universe. In his view, the cosmos was finite and spherical, with Earth at the center, surrounded by concentric celestial spheres. These spheres, which were thought to contain the celestial objects like the moon, sun, planets, and fixed stars, were believed to move in perfect circular orbits. The perfect circularity of these orbits mirrored the perceived unchanging, eternal nature of the heavens. Aristotle's model was based not only on physical observations, but also on his philosophical convictions. He posited the existence of a fifth element, known as ether, which made up the celestial realm, distinct from the 4 terrestrial elements: earth, water, air, and fire. The idea of ether was intended to explain the divine, immutable nature of the celestial bodies, in contrast to the mortal, changeable nature of the earth below. His cosmology, though remarkably intricate for its time, would dominate Western thought for centuries. This geocentric view was refined further by the Greek astronomer Claudius Ptolemy, who lived in the 2nd century CE. Ptolemy's Almagest presented a sophisticated and highly detailed mathematical system aimed at predicting the positions of celestial bodies. His model introduced the concept of epicycles, small circular orbits that planets followed while moving along larger circular paths, known as deferents. This complex arrangement was designed to explain the observed retrograde motion of the planets, when they appear to move backward in the sky for a time. Although Ptolemy's system was not perfectly accurate, it offered a working model that could explain most of the astronomical observations of his time, and was adopted across the known world for over a millennium. Meanwhile, in the medieval Islamic world, scholars like al-Battani and al-Tusi would refine and extend Ptolemy's theories, making more precise observations and corrections to earlier errors. Al-Tusi, for example, developed the Tusi couple, a geometric model that improved the mathematical descriptions of planetary motion within the Ptolemaic framework. Nevertheless, these Islamic astronomers continued to work within the constraints of the geocentric model. The geocentric worldview remained deeply embedded in the philosophical and religious doctrines of the time, influencing all cosmological interpretations. During this period, religious texts, particularly those from the Judeo-Christian tradition, also shaped cosmological thought. The Book of Genesis, for example, presents a view of the universe as a creation of a divine being. In this view, God created the heavens and the earth in 6 days, with humanity occupying a central and unique role in the grand order of creation. This theological perspective strongly influenced medieval European scholars, who harmonized Ptolemaic astronomy with biblical teachings. The result was a God-centered view of the universe, where everything had its place within a divine, orderly structure. At the same time, in the East, ancient Indian and Chinese traditions offered their own cosmological frameworks. Hindu cosmology, for instance, saw the universe as cyclic, with endless cycles of creation, preservation, and destruction overseen by deities such as Brahma, Vishnu, and Shiva. This view of cosmic cycles emphasized the constant renewal and destruction of the universe. In contrast, traditional Chinese cosmology, influenced by the philosophies of Taoism and Confucianism, focused on the concept of balance, particularly the dynamic interplay between the forces of yin and yang. The universe was seen as an ever-changing equilibrium, where opposite forces constantly interacted, maintaining cosmic harmony. While these ancient and medieval cosmological models were diverse in their structure and cultural contexts, they shared common themes of cosmic order, balance, and interconnectedness. These ideas formed the bedrock of human understanding of the universe for centuries, providing a stable framework until the paradigm shifts of the Renaissance and Enlightenment slowly dismantled these ancient models. The work of Copernicus, Kepler, Galileo, and Newton gradually replaced the geocentric worldview with the heliocentric model and a deeper understanding of the mechanics of the universe. As the scientific revolution unfolded, the focus shifted from Earth to the Sun as the center of the solar system, and eventually to a vast, expanding universe. The groundbreaking work of Isaac Newton, who formulated the laws of motion and universal gravitation, laid the foundation for a new physics that would describe the behavior of the cosmos in ways that Aristotle could never have imagined. Yet, even Newton's theories, while revolutionary, were but a stepping stone to an even more radical shift in our understanding of the universe. Today, the Big Bang Theory stands as the leading scientific explanation for the origin and evolution of the cosmos. According to this theory, the universe began roughly 13.8 billion years ago from a singularity, a point of infinite density and heat where all matter, energy, space, and time were concentrated. This singularity then underwent an extraordinarily rapid expansion, not an explosion in the traditional sense, but a sudden and vast stretching of space-time itself. As the universe expanded, it began to cool, allowing the formation of subatomic particles and the simplest elements. In the first few minutes during a period known as nucleosynthesis, protons and neutrons combined to form the nuclei of hydrogen, helium, and trace amounts of lithium. The universe remained a hot, dense place with light unable to travel freely due to constant interactions with particles. It wasn't until approximately 380,000 years after the Big Bang that the universe had cooled enough for electrons to combine with nuclei to form neutral atoms in a process called recombination. This moment marked a significant transition, allowing photons, or light, to travel freely through space. The radiation released during this time can still be detected today as the cosmic microwave background, CMB, radiation, a faint but ubiquitous glow that permeates the entire universe. This glow serves as one of the strongest pieces of evidence supporting the Big Bang Theory, as it is a direct remnant of the early universe. Over billions of years, the universe continued to expand, and the gravitational pull between particles led to the formation of stars and galaxies. These early galaxies began to cluster into even larger structures, influenced by the mysterious force known as dark matter. Dark matter, which does not emit or absorb light, interacts only through gravity, shaping the large-scale structure of the universe in ways that are still not fully understood. Today, the expansion of the universe continues, accelerated by another enigmatic force, dark energy. This strange energy, which makes up much of the universe's content, drives the accelerated expansion, causing distant galaxies to recede faster as time progresses. The observation of this expansion, first noted by Edwin Hubble and described by Hubble's law, provides a cornerstone for the Big Bang model, confirming that the universe is not static, but is continually evolving and expanding. The Big Bang Theory, alongside evidence from multiple fields of astronomy, cosmology, and physics, has transformed our understanding of the universe. What was once a static, geocentric view of the cosmos has now been replaced by a dynamic, ever-changing universe, stretching across vast scales of time and space. From Aristotle's Earth-centered spheres to the vast expanse of the universe revealed by modern science, the journey of understanding our place in the cosmos has been long and continually evolving. The Big Bang Theory stands as the leading explanation for the origins and evolution of our universe, offering a comprehensive and testable framework that is continually refined by new observations and theoretical advancements. At its core, the theory proposes that the universe began as an extremely hot and dense point, and over the course of roughly 13.8 billion years, it has expanded and evolved into the cosmos we observe today. This expansive theory is not only supported by extensive empirical evidence, but also provides a foundation for exploring the complex and awe-inspiring narrative of cosmic evolution, from the fiery beginnings of the universe to its present state and beyond. One of the most compelling aspects of the Big Bang Theory is its ability to explain observable phenomena across a variety of scales. The theory's predictions align closely with key observations, such as the relative abundance of light elements like hydrogen, helium, and trace amounts of lithium. These elements are thought to have been formed in the first few minutes following the Big Bang, during a process known as Big Bang nucleosynthesis. The predicted ratios of these elements, about 75% hydrogen and 25% helium by mass, match remarkably well with their observed levels in the oldest stars and gas clouds, adding weight to the theory's validity. Equally important is the theory's ability to account for the cosmic microwave background, CMB radiation, a faint, pervasive glow that permeates the entire universe. First discovered in 1965 by Arno Penzias and Robert Wilson, this radiation is considered the afterglow of the Big Bang. The CMB provides a snapshot of the universe approximately 380,000 years after the Big Bang, a time when the universe had cooled sufficiently for photons to travel freely through space for the first time. Subsequent measurements of the CMB, especially from missions such as COBE, WMAP, and Planck, revealed that the universe's temperature is nearly uniform, with slight fluctuations. These tiny variations represent the early seeds of all current cosmic structures, offering critical insight into the initial conditions that led to the formation of galaxies and larger cosmic structures. Another fundamental pillar supporting the Big Bang theory is the observable expansion of the universe. In the 1920s, astronomer Edwin Hubble observed that galaxies are moving away from us, with more distant galaxies receding at faster rates. This phenomenon, now known as Hubble's law, strongly suggests that the universe is expanding and implies that all galaxies were once much closer together in the distant past. The relationship between the distance of galaxies and their redshift, where light from galaxies shifts toward the red end of the spectrum as they move away from us, provides direct evidence of this expansion. This observation aligns precisely with predictions made by the Big Bang model, further reinforcing its credibility. In addition to these key pieces of evidence, the large-scale structure of the universe itself supports the Big Bang theory. Observations of galaxy clusters and the intricate cosmic web reveal that galaxies are not randomly distributed. Instead, they form a vast network of filaments and voids that mirror the fluctuations seen in the CMB. These structures likely arose from the gravitational collapse of initial density variations in the early universe, just as predicted by the Big Bang model. Together, these diverse lines of evidence create a consistent, robust picture of a universe that has been expanding and evolving for billions of years. Yet the story of the Big Bang theory is not just a tale of observed facts. It is also one of intellectual discovery, shaped by a long history of theoretical insights and groundbreaking observations. The acceptance of the Big Bang theory by the scientific community was not instantaneous. It was the result of decades of gradual development, marked by key milestones that ultimately coalesced into the paradigm we embrace today. The journey began in the early 20th century, when Albert Einstein's theory of general relativity revolutionized our understanding of gravity, space, and time. In 1917, Einstein applied his equations to the universe as a whole, but initially introduced a cosmological constant to maintain a static universe, a belief that was widely held at the time. However, in the 1920s, astronomer Edwin Hubble made a groundbreaking discovery that forever changed our understanding. Galaxies were moving away from us. This observation implied that the universe was not static but expanding, contradicting the prevailing notion of an eternal, unchanging cosmos. At nearly the same time, Russian physicist Alexander Friedmann and Belgian priest astronomer Georges Lemaitre independently proposed models of an expanding universe derived from solutions to Einstein's equations that did not rely on the assumption of a static cosmos. Lemaitre, in particular, introduced the concept of a primeval atom, a highly concentrated initial state from which the universe began to expand. Despite these new insights, the idea of a dynamic, evolving universe was met with skepticism and resistance in certain quarters. In the mid-20th century, the scientific community was presented with an alternative model, the Steadystate theory. British astrophysicist Fred Hoyle and his colleagues proposed that the universe was in a constant state of creation, with matter continuously generated to explain the observed expansion, all while maintaining a constant average density. Despite its initial popularity, this theory lost ground in the face of new discoveries that provided powerful support for the Big Bang. In 1948, scientists Ralph Alpher and George Gamow predicted that the early universe would have been hot and dense enough to create light elements through nucleosynthesis. This led to the calculation of hydrogen and helium ratios, which matched those observed in the oldest stars and gas clouds, providing further support for the Big Bang model. The most significant breakthrough, however, came in 1965 when Penzias and Wilson's discovery of the CMB confirmed the Big Bang's hot, dense origins. The CMB was a relic of the universe's earliest moments, offering tangible evidence of its explosive birth. This discovery, in turn, sparked a shift in scientific consensus, with many adopting the Big Bang theory as the most plausible explanation for the universe's origins. Further refinements to the theory came in the form of satellite missions such as COBE, WMAP, and Planck, which mapped the CMB with increasing precision. These measurements revealed the tiny temperature fluctuations in the CMB that correspond to the seeds of large-scale cosmic structures, galaxies, clusters, and the vast cosmic web that we observe today. Today, the Big Bang theory is not only the dominant cosmological model, but also one that continues to evolve as we make new discoveries. With ongoing advancements in both technology and theoretical research, scientists are piecing together an ever more detailed chronology of the universe's history, from its fiery birth to its current state and into the future. The evidence supporting the Big Bang theory is vast and multifaceted, forming a compelling, consistent narrative of cosmic evolution. It remains, without a doubt, one of humanity's greatest scientific achievements in our quest to understand the origins of the universe itself. The late 1990s brought a remarkable revelation to the field of cosmology: the discovery of the universe's accelerating expansion, attributed to a mysterious force known as dark energy. This groundbreaking finding, coupled with an array of other pivotal discoveries, further solidified the Big Bang theory as the dominant model for explaining the origins and evolution of the cosmos. As evidence mounted, the Big Bang theory emerged as a comprehensive framework that unified observations of the universe's vast structure, the abundance of light elements, and the cosmic microwave background, CMB. The convergence of these theoretical predictions and empirical data culminated in the widespread acceptance of the Big Bang theory within the scientific community, profoundly shaping our understanding of the universe's inception and its subsequent evolution. The story of the universe's birth begins not with a loud explosion, as its name might suggest, but with a rapid and profound expansion, a phenomenon that unfolded with unimaginable speed. This event, known as the Big Bang, occurred approximately 13.8 billion years ago. At that moment, the entire universe existed in a singularity, a point so dense and hot that it was vastly smaller than the tip of a pin. The earliest stage of the Big Bang is known as the Planck epoch, lasting a mere fraction of a second, about 10 to the power of negative 43 seconds after the universe's inception. During this incredibly brief period, the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were all unified. The conditions were so extreme that conventional physics as we know it today was unable to describe them, necessitating a synthesis of quantum mechanics and general relativity, a task that remains elusive to physicists even in the present day. As the universe expanded and cooled, it transitioned into the inflationary epoch, an astonishingly brief phase that occurred around 10 to the power of negative 36 seconds after the Big Bang. In this epoch, the universe underwent rapid, exponential expansion, causing space itself to stretch faster than the speed of light. Remarkably, this expansion was not the result of matter moving through space, but rather the stretching of the very fabric of space itself, a process that defies our everyday experiences and intuitions. From there, the universe entered the quark epoch, a period spanning roughly from 10 to the power of negative 12 seconds to 10 to the power of negative 6 seconds after the Big Bang. During this time, the temperature and density of the universe began to decrease, allowing quarks, the fundamental particles that make up protons and neutrons, to form. As the universe cooled even further, quarks began to combine, forming protons and neutrons, which were the building blocks of atomic nuclei. This phase was followed by the hadron epoch, during which these particles fused to create the first light atomic nuclei, marking the onset of nuclear synthesis, a crucial moment in the universe's early history. Within the first 3 minutes after the Big Bang, the universe had already begun to form the primordial elements that would eventually give rise to atoms, stars, galaxies, and the intricate cosmic structures we see today. In those initial moments, the universe underwent a series of rapid, transformative changes. Within a fraction of a second, the cosmos was in a state of extreme density and temperature, a swirling soup of fundamental particles. As it expanded and began to cool, the different forces and particles began to differentiate, laying the groundwork for the formation of more complex structures. By the end of the first second, the universe had cooled enough to allow for the creation of quarks and leptons, including electrons. These particles began to separate from the primordial plasma, setting the stage for the formation of stable atoms in the future. During the same period, neutrinos, a class of extremely light particles that interact very weakly with matter, became transparent, traveling freely through space. This event is detectable today in the cosmic neutrino background, a faint but significant imprint left from those early moments of the universe. As the universe continued to evolve, electromagnetic interactions became more prominent. Photons, the fundamental particles of light, started to play a major role. However, it would still take thousands of years for the universe to cool enough for matter and radiation to decouple completely. This decoupling would eventually allow for the formation of stable atoms and, much later, the stars and galaxies that we observe in the night sky. One of the most critical remnants from this early era is the cosmic microwave background, CMB, a relic of the universe's adolescent years. The CMB serves as a snapshot of the universe approximately 380,000 years after the Big Bang. At this time, the universe had cooled enough for atoms to form. Before this, the universe was dense and hot, with protons and electrons unable to combine. Instead, they existed in a charged plasma. However, as the universe expanded and cooled further, these charged particles combined to form neutral hydrogen atoms in a process known as recombination. Once this occurred, photons, which had been constantly scattered by free electrons, could now travel freely through space for the first time. This marked the universe's transition from an opaque fog to a transparent expanse, allowing light to travel across the cosmos uninterrupted. The CMB is the faint glow of this first light, stretched into microwave wavelengths by billions of years of cosmic expansion. The importance of the CMB cannot be overstated. It carries invaluable information about the early universe, offering a window into the conditions that existed when the universe was only a few 100,000 years old. Tiny fluctuations in the temperature and density of the CMB map out the seeds of future structures, including galaxies, clusters of galaxies, and superclusters. These fluctuations offer clues about how the universe evolved from a smooth, homogeneous state to the complex, dynamic cosmos we observe today. These variations, deeply scrutinized by advanced satellite missions like Cobra WX and Planck, reveal not only the age and composition of the universe, but also provide vital support for the Big Bang theory itself. By studying the cosmic microwave background, CMB, cosmologists can test predictions about the universe's earliest moments, unlocking crucial insights into its origins, large-scale structure, and the fundamental physical laws that govern its evolution. Observing the afterglow of the Big Bang, known as the CMB, is like peering back through time, offering a rare glimpse of the universe in its infancy. This faint radiation permeates the entire cosmos, detectable in all directions, and is surprisingly uniform, with only minute fluctuations that hold a wealth of information about the universe's past. To detect and study this ancient light, scientists rely on specialized instruments, both on the ground and in space, finely tuned to detect the microwave portion of the electromagnetic spectrum. Space missions have been particularly instrumental in this quest, with satellites like the Cosmic Background Explorer, COB, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite taking the lead. COB, launched in 1989, was the pioneering mission that provided the first precise measurements of the CMB's temperature and spectrum, confirming it as the relic radiation from the Big Bang. WMAP, which launched in 2001, followed up with a more detailed map of temperature fluctuations, refining our understanding of the universe's age, composition, and development. But the most accurate measurements to date come from the Planck satellite, launched in 2009. Planck's highly sensitive instruments allowed scientists to measure the CMB's temperature variations with unprecedented precision, enabling cosmologists to test theories about the universe's initial conditions and the elusive nature of dark matter and dark energy. In addition to these space missions, ground-based observatories, often located at high altitudes or in remote regions like Antarctica, provide crucial supplemental data. Places such as the Atacama Desert in Chile and the South Pole offer pristine conditions free from atmospheric interference, ideal for studying the CMB. Projects like the Atacama Cosmology Telescope, ACT, and the South Pole Telescope, SPT, continue to provide invaluable data, contributing to the three-dimensional map of the universe's structure and its evolution over time. Through these sophisticated and coordinated efforts, the afterglow of the Big Bang has evolved from a distant relic to a powerful tool, illuminating the mysteries of our cosmic origins and the fundamental forces that have shaped the universe as we know it. Quantum fluctuations represent one of the most fascinating and profound phenomena in the realm of quantum mechanics. These tiny temporary changes in the amount of energy at a specific point in space arise from the Heisenberg uncertainty principle, which asserts that it's impossible to precisely measure both the position and momentum of a particle at the same time. This principle suggests that the vacuum of space is not empty, but instead teems with fleeting pairs of particles and antiparticles that pop in and out of existence. These ephemeral particles briefly borrow energy from their surroundings before annihilating each other and returning the energy. These quantum fluctuations have profound implications for the structure of the cosmos. In the early universe, during the brief yet transformative period of cosmic inflation, these tiny quantum jitters were stretched out to macroscopic scales as space itself expanded exponentially. These fluctuations seeded tiny variations in density that would later grow into the vast cosmic structures we observe today. It's these minute differences, amplified by inflation, that eventually led to the large-scale distribution of matter, forming galaxies, clusters of galaxies, and cosmic voids, the fingerprints of quantum fluctuations embedded in the CMB. The slight temperature fluctuations we observe in the CMB are essentially the magnified echoes of these early quantum jitters, preserved from the dawn of time. In this way, quantum mechanics doesn't just govern the behavior of particles at the smallest scales, it also plays a critical role in shaping the very large-scale structure of the universe. By studying these fluctuations, scientists continue to unravel the complex interplay between quantum forces and cosmic evolution, gaining deeper insights into the fundamental workings of reality itself. Quantum fluctuations, these tiny ephemeral tremors in the fabric of space-time, hold the remarkable ability to catalyze the creation of particles in a variety of fascinating ways. At their core, quantum fluctuations arise from the Heisenberg uncertainty principle, a fundamental concept of quantum mechanics that implies the vacuum of space is anything but empty. Instead, it is a dynamic expanse, constantly brimming with transient bursts of energy. One of the most significant ways quantum fluctuations contribute to particle creation is through a process known as pair production. During pair production, energy borrowed from the quantum vacuum materializes as a particle-antiparticle pair. These pairs typically annihilate each other almost instantly, returning the borrowed energy. However, in the presence of a strong electromagnetic field, such as near the event horizon of a black hole or within the high-energy environment of a particle accelerator, these pairs can be separated before they annihilate. If the particle-antiparticle pair gains enough energy from its surroundings, it can become a real, lasting particle, contributing to the observable matter in the universe. Thus, these seemingly insignificant quantum fluctuations, governed by the uncertainty principle, can have profound consequences for the very nature of reality, influencing everything from the smallest particles to the largest cosmic structures. The universe, in its early moments, was vastly different from what we see today. It was a place of intense energy, where space itself expanded at extraordinary rates in an event known as cosmic inflation. During this rapid expansion, quantum fluctuations, tiny, fleeting variations in energy, were stretched to unimaginable scales, becoming macroscopic phenomena. These fluctuations caused subtle disturbances in the energy field that permeated all of space. As the universe cooled, these perturbations evolved, leading to regions of slightly higher and lower energy densities across the cosmos. In the areas where energy density was higher, the conditions were ideal for transforming this energy into particles, an event known as reheating. This process essentially turned the energy stored in quantum fluctuations into a dense, hot soup of particles, a primordial brew that laid the foundation for the universe as we know it. This moment, often referred to as the genesis of the universe, seeded the cosmos with the matter and radiation that would eventually give rise to stars, galaxies, and all the structures we observe today. Thus, quantum fluctuations did far more than just momentarily disturb the vacuum of space. They played a crucial role in the creation of the universe itself, directly influencing the birth and evolution of the cosmos. This highlights a deeper, almost poetic relationship between the quantum realm and the large-scale structure of the universe, revealing an interconnectedness that underpins the very nature of reality. At the heart of these cosmic processes lies the concept of vacuum energy, a strange and paradoxical idea. On the surface, a vacuum might seem like nothingness, an empty void devoid of matter and radiation. In classical physics, a vacuum is thought to be an absolute void, a true emptiness. However, quantum mechanics paints a very different picture. Even in the most seemingly empty stretches of space, activity is constantly occurring due to the ceaseless dance of virtual particles. These virtual particles constantly pop in and out of existence, creating a fluctuating sea of energy fields. This persistent underlying activity contributes to a baseline level of energy known as vacuum energy. It is this energy that permeates all of space, even where no particles or radiation exist. The existence of vacuum energy is intimately tied to the Heisenberg uncertainty principle, which suggests that energy levels within any given point in space can never truly be zero. In other words, there is always some form of energy, even in what we perceive as a perfect vacuum. This notion has profound implications for our understanding of the universe. One of the more fascinating manifestations of vacuum energy can be observed through the Casimir effect. When two uncharged parallel metal plates are placed incredibly close together in a vacuum, they experience an attractive force, even though there is no conventional electromagnetic interaction at play. This force arises from the difference in the density of virtual particles between the plates and in the surrounding vacuum. This subtle yet tangible effect provides a glimpse into the invisible influence of vacuum energy, demonstrating how the universe is far from empty, even in the absence of matter. Vacuum energy also plays a crucial role in modern cosmology, particularly when we turn our attention to the mysterious phenomenon of dark energy. Observations of distant supernovae and measurements of the cosmic microwave background radiation reveal that the universe is not only expanding, but its expansion is accelerating. This accelerated expansion could be driven by a form of vacuum energy known as dark energy. Dark energy, which constitutes approximately 70% of the total energy content of the universe, is thought to be a manifestation of vacuum energy that exerts a repulsive force, counteracting the pull of gravity and driving galaxies apart at an ever-increasing rate. This realization reshapes our understanding of the cosmos. What we once thought of as a seemingly empty vacuum is now understood to be a rich and active field, influencing the structure and evolution of the entire universe. From the Casimir effect to the accelerating expansion of the universe, vacuum energy is a testament to the profound and often counterintuitive nature of the quantum world. In fact, vacuum energy is fundamentally tied to the universe's very origins. In the earliest moments after the Big Bang, the universe was in a state of extreme heat and density, where classical physics no longer applied and quantum mechanics took center stage. During this time, a scalar field, often referred to as the inflaton field, dominated the dynamics of the cosmos. This field, a form of vacuum energy, was not connected to any particles or radiation. Instead, it was linked to the very fabric of space-time itself. The energy from the inflaton field generated a repulsive force that triggered the rapid exponential expansion of space, an event known as cosmic inflation. This period of inflation smoothed out any irregularities and homogenized the observable universe, setting the stage for the formation of the structures we see today. As the universe expanded, quantum fluctuations in the vacuum energy field were stretched to cosmic scales, seeding tiny density variations that would eventually give rise to the galaxies, clusters of galaxies, and the cosmic web we observe in the universe's large-scale structure. These fluctuations were the starting points for the universe's evolution, highlighting how even the smallest quantum phenomena can have profound implications for the cosmos at large. As inflation came to an end, the vacuum energy of the inflaton field began to decay. This decay process converted the energy into a hot, dense plasma of particles in an event known as reheating. Reheating marked the transition from the inflationary era to the hot Big Bang phase, setting the stage for the universe as we know it today. The connection between vacuum energy and the cosmos origin underscores the pivotal role quantum mechanics plays in shaping the universe. In the early moments after the Big Bang, it was this energy, interwoven into the very fabric of space, that set the universe on its evolutionary path, ensuring that the energy fluctuations of the quantum world would ultimately seed the formation of galaxies, stars, and everything in between. Thus, quantum fluctuations, vacuum energy, and dark energy are not isolated concepts, but are deeply interwoven in the story of the universe. These forces, so far removed from our everyday experiences, influence the most fundamental processes of the cosmos, from the birth of particles to the accelerating expansion of the universe. They remind us that the universe we live in is shaped not only by the forces we can observe, but by the hidden realms of the quantum world, where the rules of classical physics break down and the mysteries of existence unfold. The energy released during the birth of the universe served as the essential fuel for the processes that followed, igniting the creation of matter and radiation. This surge of energy left an indelible mark on the early universe, laying down the intricate blueprint for its ongoing expansion. In the grand scheme of cosmic history, vacuum energy is far from a mere abstract idea. It is a key player in the narrative of the universe's evolution. It played a pivotal role in the rapid early expansion of space, setting the initial conditions for the structures we see in the cosmos today. Furthermore, it helped ease the transition from a universe dominated by quantum fluctuations to the classical universe filled with matter and radiation. Through these profound contributions, vacuum energy highlights the intricate connection between the quantum world and the vast expanse of the universe. Each realm, quantum and cosmic, interacts with the other in ways that continue to challenge and captivate our understanding of existence. The idea that something can arise from nothing, propelled by the laws of quantum mechanics, is one of the most fascinating and paradoxical concepts in modern physics. At the core of this intriguing notion is the quantum vacuum. Far from being an empty, inert void, the quantum vacuum is alive with a seething, dynamic energy. Within it, virtual particles flicker in and out of existence, constantly fluctuating in response to the underlying uncertainty of quantum mechanics. According to the Heisenberg uncertainty principle, the exact energy of any point in space cannot be known with absolute precision. This means that the quantum vacuum is never truly empty. It is a constantly fluctuating sea of energy. These fluctuations give rise to pairs of particles and antiparticles that exist for mere moments before annihilating each other. For that brief instant, they bring to life the curious idea that something can indeed emerge from nothing. The Casimir effect provides experimental support for this phenomenon. In this effect, two metal plates placed close together in a vacuum alter the vacuum energy between them, creating a measurable force that proves the existence of virtual particles. On a cosmic scale, these quantum fluctuations may have played a crucial role in the birth of the universe itself. The theory of cosmic inflation suggests that during the universe's earliest moments, these fluctuations were stretched to vast scales, ultimately giving rise to the large structures we observe today, such as galaxies and clusters of galaxies. Moreover, modern cosmology suggests that the universe may have originated from a quantum state, driven by fluctuations in a foundational quantum field. This concept aligns seamlessly with the idea of vacuum energy, energy that is inherent in the fabric of space, even in the absence of matter and radiation. Leading physicists like Stephen Hawking have proposed that universes could spontaneously emerge from this quantum vacuum, driven by fluctuations similar to those responsible for virtual particles. This idea opens the door to the theory of the multiverse, a universe composed of countless individual universes, each with its own distinct set of physical laws. While the multiverse theory remains speculative and beyond the reach of direct observation, it provides an intriguing framework for understanding how our own universe may have arisen from a quantum fluctuation. Thus, within the realm of quantum mechanics, the idea that something can emerge from nothing is not just a philosophical curiosity, but a scientifically plausible possibility. It challenges our classical understanding of reality and raises profound questions about the nature of existence itself. The boundary between something and nothing may not be as rigid as we once believed. It could, in fact, be far more porous and fluid than previously imagined. Virtual particles are one of the most fascinating and elusive concepts in quantum mechanics. They are not particles in the conventional sense. Rather, they are transient fluctuations that appear and disappear within the quantum vacuum. These particles are far from permanent or tangible. They only exist for fleeting moments, defying the classical idea of particles as stable, observable entities. The very existence of virtual particles is a direct manifestation of the Heisenberg uncertainty principle, which allows for a certain degree of uncertainty in energy and particle existence, particularly over very short scales. Despite their ephemeral nature, virtual particles play a profound and diverse role in the universe. They are essential to the forces that govern the interactions between particles. For example, in quantum electrodynamics, QED, the electromagnetic force between charged particles like electrons is mediated by virtual photons. These photons, although never directly observed, are responsible for the force we observe between charged particles. Similarly, virtual particles like the W and Z bosons mediate the weak nuclear force, which governs radioactive decay. Gluons, another type of virtual particle, are responsible for the strong nuclear force, which binds quarks together to form protons and neutrons. Virtual particles also leave observable consequences in the form of phenomena like the Casimir effect. When two uncharged parallel metal plates are placed very close together in a vacuum, the difference in vacuum energy between the plates and the surrounding space generates a measurable attractive force. This force is a tangible manifestation of the presence of virtual particles, even though they themselves are undetectable. The role of virtual particles extends to the mysterious depths of black holes. According to Stephen Hawking's groundbreaking theory of Hawking radiation, near the event horizon of a black hole, pairs of virtual particles can be separated by the immense gravitational forces at play. One particle falls into the black hole, while the other escapes into space as real radiation. This process leads to the gradual loss of mass and energy from the black hole, eventually causing it to evaporate over vast cosmic timescales. Additionally, virtual particles are integral to the concept of vacuum polarization in quantum field theory. In this process, the presence of a charged particle in the vacuum temporarily creates pairs of virtual electron-positron pairs, which modulate the charge distribution around the particle. This in turn alters the observed charge and the electromagnetic interactions associated with it. In summary, virtual particles may be fleeting and undetectable on their own, but their role in the universe is indispensable. From mediating the fundamental forces of nature to enabling the phenomena of black hole radiation, virtual particles are a hidden but vital component of the quantum world. They serve as the bridge between the abstract mathematical models of quantum mechanics and the physical effects we observe in the real world. They are the unseen scaffolding that supports the laws of the universe, allowing it to function in ways that classical physics could never have predicted. The pursuit of understanding the origins of the universe has given rise to a variety of cosmological models, each offering distinct perspectives on how the cosmos began and evolved. These models combine empirical observations with theoretical frameworks, ranging from classical theories to more speculative propositions grounded in the latest advances in physics. Among these models, the Big Bang Theory stands as the most widely accepted and scientifically robust explanation for the birth of the universe. According to this model, the universe began roughly 13.8 billion years ago from an incredibly hot and dense singularity. Since that moment, the universe has been expanding, cooling, and evolving into the vast, diverse cosmos we observe today. The origin and evolution of the universe have long captivated the curiosity of scientists and thinkers alike. Central to this inquiry is the Big Bang Theory, which suggests that the universe began as an incredibly hot and dense point approximately 13.8 billion years ago, rapidly expanding and cooling over time to form the cosmos we observe today. However, the Big Bang Theory is not the only contender in this vast intellectual arena. Alongside it, a number of alternative theories seek to explain the universe's origin and its subsequent evolution, each contributing unique perspectives. One of the most compelling pieces of evidence supporting the Big Bang Theory comes from the cosmic microwave background, CMB radiation, an afterglow from the early universe. The CMB is a faint, uniform radiation that fills the universe, providing a snapshot of the cosmos when it was just 380,000 years old. It is often referred to as the fossil radiation of the Big Bang. In addition to this, the abundance of light elements, particularly hydrogen and helium, observed throughout the universe supports the idea that these elements were formed in the first few minutes following the Big Bang, during a process known as Big Bang nucleosynthesis. Moreover, the redshift of distant galaxies, the phenomenon in which light from distant objects shifts to longer wavelengths, further corroborates the theory. This redshift indicates that the universe is expanding, causing galaxies to move away from each other, a key prediction of the Big Bang model. Building on this, the theory of cosmic inflation, proposed by physicist Alan Guth in the early 1980s, expands the Big Bang theory to offer a more detailed explanation of the universe's early moments. According to this inflationary model, the universe underwent a rapid exponential expansion within a fraction of a second after the Big Bang. This brief but intense period of inflation is thought to have smoothed out any initial irregularities in the cosmos, explaining the large-scale uniformity of the universe. It also accounts for the tiny fluctuations in the CMB that eventually gave rise to galaxies and larger cosmic structures. Inflation helps address questions about the uniformity and the fine-tuning of the universe. However, not all cosmological models agree with the Big Bang theory. One notable alternative is the Cyclic model, which posits that the universe undergoes endless cycles of expansion and contraction. In this view, the Big Bang is not a unique event, but rather a recurring phenomenon driven by the complex physics of cosmic brains in higher dimensional space, as described by string theory. According to the Cyclic model, each cycle of expansion and contraction could trigger new instances of cosmic birth and death, with the universe continually being reborn in a repetitive process. One specific variant of this model, known as the ekpyrotic universe, suggests that these cycles are the result of collisions between brains, offering a novel take on the evolution of the cosmos. While the Cyclic model is certainly more speculative than the Big Bang theory, it provides an intriguing framework for understanding some of the fundamental puzzles of cosmology, such as the nature of dark energy and the origins of the universe's initial conditions. It offers an alternative vision of a universe that is not bound to a singular origin, but rather follows an ongoing, eternal rhythm of birth, death, and rebirth. In contrast, the Steadystate theory, once a popular rival to the Big Bang theory, argues that the universe has no true beginning or end. Instead, it maintains a constant average density, despite the ongoing expansion of space. First proposed in 1948 by Fred Hoyle, Thomas Gold, and Hermann Bondi, the steady-state model suggests that as the universe expands, new matter is continuously created to fill the voids left behind. This process occurs at an incredibly slow rate, around 1 hydrogen atom per cubic meter per billion years, making it undetectable by current observational techniques. Under this theory, the universe is eternal, unchanging on large scales, and appears the same at any given time. However, the steady-state theory eventually fell out of favor due to its inability to account for critical observations, most notably the discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson. This discovery provided powerful evidence for the Big Bang model, revealing the faint radiation left over from the early, hot state of the universe. The uniformity of the CMB strongly aligns with the Big Bang theory, which posits that this radiation is the residual heat from the universe's infancy. Another fascinating proposal comes from quantum mechanics. The idea of a quantum creation of the universe suggests that the cosmos could have spontaneously emerged from a quantum vacuum fluctuation. According to this model, the universe originated from a state of nothing, driven by the principles of quantum physics. This idea was championed by physicists such as Stephen Hawking and James Hartle, who introduced the no-boundary condition. This concept suggests that time behaves similarly to a spatial dimension at the universe's inception, smoothing out any singularity and allowing for the emergence of a universe from nothing. In this framework, the universe could be seen as a quantum phenomenon, birthed from the laws of physics themselves. Taking the concept of parallel realities to a new level, the multiverse hypothesis proposes that our universe is just one of potentially infinite parallel universes. These universes could exist within a broader, multidimensional multiverse, each with its own set of physical constants and laws. The multiverse theory is often tied to interpretations of inflationary theory and string theory, with the idea that different regions of space may inflate at different rates, creating distinct universes. These universes could be causally disconnected, each following its own unique trajectory. The multiverse hypothesis, though highly speculative, challenges our fundamental understanding of reality, suggesting that the universe we observe may not be the only one that exists. In conclusion, while the Big Bang Theory, bolstered by the concept of cosmic inflation, remains the dominant model explaining the origin and evolution of the universe, other theories continue to spark debate and exploration. The cyclic universe, steady-state theory, quantum creation, and multiverse hypothesis all offer alternative or complementary views of cosmic origins. Together, these cosmological models reflect humanity's ongoing quest to decode the mysteries of the cosmos, each contributing valuable insights while also raising new, profound questions about the nature of existence and the ultimate origins of our universe. These models challenge us to think beyond our own reality and explore the deeper, unknown layers of the universe's grand narrative. The vastness of the cosmos, with its countless galaxies, stars, and mysterious phenomena, continues to ignite humanity's imagination. One of the most captivating aspects of our exploration of the universe lies in the compelling theories that attempt to explain its origin and evolution. Among these theories, the Big Bang Theory stands out, offering a coherent narrative supported by a wealth of observational evidence, which paints a picture of a universe that has evolved over time. Observations of distant galaxies and quasars bolster this view, supporting the idea that the universe is constantly evolving. The Big Bang Theory offers a robust framework to explain this, suggesting that the universe once existed in a far more compact and active state, with galaxies in their infancy and star formation occurring at a frenetic pace. In stark contrast, the steady-state theory, which posits a constant and unchanging cosmos, cannot account for the observed changes in galactic structures or the accelerated rate of star formation. This theory, which maintains that new matter is continuously created to preserve a steady state of the universe, fails to explain key findings such as the cosmic microwave background radiation, the remnant heat from the Big Bang, and the observable evolution of galaxies over time. The Big Bang Theory, by contrast, offers a comprehensive explanation. It suggests that the universe began from an incredibly hot and dense state and has been expanding and cooling ever since. This theory not only accounts for the phenomena observed, but also fits neatly into the framework of modern cosmology, where the evolution of galaxies, the distribution of matter, and the expansion of space are all tied to a common origin point, the Big Bang. However, there is also a more speculative alternative, the cyclic model. Unlike the traditional view of a singular beginning followed by an ever-expanding universe, the cyclic model envisions the universe as undergoing endless cycles of birth, evolution, and rebirth. These cycles could span enormous timescales, stretching over hundreds of billions or even trillions of years, resulting in a cosmos that perpetually renews itself. In this framework, the universe experiences an eternal series of expansions and contractions, where each cycle ends in a big crunch before giving way to a new Big Bang, a fiery rebirth from destruction. One of the most intriguing cyclic models is the ekpyrotic universe, which draws inspiration from string theory and higher dimensional cosmology. In this model, our universe is conceived as a three-dimensional brane, short for membrane, embedded in a higher dimensional space. Every so often, this brain collides with another parallel brain, releasing massive amounts of energy that initiate a new cycle of expansion. This collision sets off a new Big Bang-like event, leading to the creation of new matter and radiation, much like the start of a new cycle. The term ekpyrotic is derived from the Greek word for conflagration, symbolizing the intense and fiery nature of these cosmic rebirths. The cyclic model offers intriguing explanations for several of the most puzzling issues in cosmology. For example, each contraction phase could erase the irregularities and anisotropies, or unevenness, observed in the structure of the universe, much like the inflationary period in the traditional Big Bang model. This would ensure that each new cycle begins with a smooth, homogeneous, and isotropic universe. Additionally, the cyclic framework provides a potential resolution to the cosmological constant problem, which describes the energy density of the vacuum and drives the accelerated expansion of the universe. In the cyclic context, this constant could be dynamically adjusted during each cycle, alleviating the fine-tuning issues that plague other models. Yet, despite its potential, the cyclic model also presents significant challenges. One of the primary concerns is how each cycle can transition smoothly from contraction to expansion without resulting in a singularity, a point of infinite density where conventional physics breaks down. Addressing this conundrum requires the development of advanced mathematical models and a deeper understanding of quantum gravity and string theory. Moreover, the cyclic model must reconcile with observational data such as the cosmic microwave background, CMB, radiation, which has traditionally been interpreted within the framework of a single expanding universe. The model must not only reproduce existing observations, but also make new testable predictions that can be verified through astrophysical measurements. As theoretical physics advances, the cyclic model could either find empirical support or fall short in explaining the universe's true nature. Either way, it contributes to a broader conversation about the cosmos and our place within it. In this way, the cyclic model serves as a fascinating alternative, suggesting a universe in a constant state of renewal, where each cycle brings with it new possibilities, challenges, and mysteries to unravel. Meanwhile, another radical theory about the cosmos's nature takes the concept of multiple universes to an entirely new level: the multiverse theory. This theory proposes that our universe is just one of a potentially infinite number of universes that exist in a vast and possibly infinite multiverse. Each of these universes may operate under entirely different physical laws, constants, and conditions, leading to a diverse range of possibilities for what might constitute a universe. The idea of the multiverse emerges from several different strands of theoretical inquiry, including cosmic inflation, string theory, and quantum mechanics, each offering a unique perspective on how multiple universes could arise. One of the most compelling versions of the multiverse theory comes from the concept of eternal inflation, which builds upon the inflationary model of the Big Bang. In this view, cosmic inflation, the rapid expansion of space in the moments after the Big Bang, never truly ceases, but continues in isolated pockets of space. These pockets, or bubble universes, eventually cease inflating and form separate universes, each with its own distinct properties. This leads to a vast, diverse multiverse, where our universe is merely one bubble among an infinite number of possibilities. String theory provides another fertile ground for the development of the multiverse concept. Within the framework of string theory, the landscape of possible universes is vast, with each configuration corresponding to a potential universe with its own set of physical laws and constants. These configurations arise from the different ways in which extra dimensions, as proposed by string theory, can be compactified. The idea is that the different ways these extra dimensions could be arranged lead to a variety of possible universes, each with its own unique set of physical laws. Additionally, the many worlds interpretation of quantum mechanics presents a form of the multiverse, where every quantum event that could potentially occur does, but in separate, non-communicating branches of reality. In this view, every decision, every random event, leads to the splitting of the universe into parallel versions, each representing a different outcome. Though this is conceptually distinct from the multiverses proposed by cosmic inflation or string theory, It adds another layer to the idea that our universe is not unique, but part of a vast ensemble of realities. The multiverse theory carries profound implications for our understanding of the universe, particularly in explaining the fine-tuning of physical constants observed in our cosmos. Many of the constants governing the behavior of matter and energy seem to be precisely set in order to allow for the existence of stars, galaxies, and life. In a multiverse containing an enormous variety of universes, it's conceivable that only a small fraction of them would have the right conditions for life as we know it. Our universe, then, could be one of the rare few where the physical constants happen to fall within a narrow range that allows for the complex structures and biological life we observe, a scenario often referred to as the anthropic principle. However, the multiverse theory is still largely speculative. Direct empirical verification remains elusive, as other universes, if they exist, would likely be causally disconnected from our own, making interaction or observation impossible with current methods of scientific inquiry. As such, the multiverse theory presents an exciting but deeply speculative possibility for the nature of reality, one that stretches the boundaries of what we can know about the cosmos. In conclusion, while theories like the Big Bang and Cyclic models provide us with frameworks to understand the origins and evolution of the universe, the multiverse theory invites us to question whether our universe is just one of countless others, each with its own distinct nature. These theories, each offering a different perspective, challenge our understanding and push the limits of theoretical physics, encouraging us to continue our quest for a deeper, more comprehensive understanding of the cosmos. However, some theoretical predictions within the multiverse framework could indirectly influence observable phenomena in our universe. These could include subtle imprints left on the cosmic microwave background, CMB from bubble collisions, or unique signatures that might appear in particle physics experiments. In conclusion, the multiverse theory suggests that our universe is just one among many, each with its own distinct properties and origins. While it offers a tantalizing potential framework for understanding both the origin and the fine-tuning of our universe, it also presents significant challenges when it comes to empirical validation. As both our theoretical models and observational technologies continue to advance, the multiverse theory stands as a compelling subject of research, positioned at the very frontier of modern cosmology and theoretical physics. Inflation theory, a cornerstone of modern cosmology, offers an elegant explanation for the rapid expansion of the universe during its earliest moments. First proposed by physicist Alan Guth in the early 1980s, this theory suggests that a brief but intense period of exponential expansion occurred just a fraction of a second after the Big Bang. This phase of inflation lasted an astronomically short amount of time, about 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds, but its impact on the universe's structure and evolution was profound. Inflation theory helps to resolve several pressing issues that arose from the traditional Big Bang model. One such issue is the horizon problem. According to the Big Bang theory, regions of the universe separated by vast distances should not have had enough time to reach the same temperature, given the finite speed of light and the relatively young age of the universe. Yet, the remarkable uniformity of the cosmic microwave background radiation, CMB, across the sky suggests that these distant regions somehow managed to come into thermal equilibrium. Inflation solves this mystery by proposing that all parts of the observable universe were once in a much smaller, more uniform space. This space was then rapidly stretched apart, allowing for the uniformity observed in the CMB. Another issue addressed by inflation is the flatness problem. Observations indicate that the universe is remarkably close to being geometrically flat, with its overall density nearly at the critical value that separates a universe that will eventually collapse from one that will continue expanding forever. For the universe to be as flat as it appears today, the initial conditions would have needed to be in an extraordinarily fine-tuned balance. The rapid expansion during inflation effectively diluted any initial curvature, like driving the universe towards flatness. This is analogous to how a small portion of a curved surface can appear flat when viewed from up close. Inflation also provides an explanation for the generation of primordial density fluctuations. Quantum fluctuations in the inflaton field, the hypothetical scalar field responsible for driving inflation, were stretched to macroscopic scales during the rapid expansion. These quantum fluctuations evolved into classical density perturbations in the distribution of matter and energy. Over time, these minute fluctuations grew under the influence of gravity, eventually leading to the formation of galaxies, clusters, and the large-scale structure of the universe that we observe today. This prediction aligns closely with the subtle temperature variations found in the CMB, which act as snapshots of these early density fluctuations. The theory of inflation has garnered substantial observational support. Detailed measurements of the CMB, particularly from satellites such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, AP, and the Planck satellite, have provided data that aligns closely with inflationary models. These observations include the uniformity and slight anisotropies in the CMB, which correspond to the density fluctuations seeded during inflation. Inflation theory also offers a seamless connection to particle physics. While the precise nature of the inflaton field remains a subject of ongoing research, various candidates have been proposed, including fields from supersymmetry and grand unified theories. These connections bridge the gap between cosmology and high-energy physics, offering a more unified view of fundamental forces and the earliest moments of the universe. In summary, inflation theory has dramatically reshaped our understanding of the universe's early expansion. It addresses critical issues such as the horizon problem, the flatness problem, and the origin of large-scale structure. With strong theoretical foundations and robust observational support, it remains a pivotal and compelling framework within cosmological studies, continuing to guide our quest to comprehend the universe's origins and evolution. In the vast, enigmatic expanse of our universe, dark matter and dark energy remain central, yet largely mysterious components. Scientists estimate that a mere 5% of the universe is composed of the visible matter that forms the stars, planets, and galaxies we see around us. The remaining 95% is split between dark matter, constituting roughly 27% of the universe, and dark energy, which makes up an astounding 68%. Despite being invisible and elusive, dark matter behaves like a cosmic scaffolding, holding galaxies together through its gravitational influence. Without dark matter, galaxies would not have the structural integrity needed to resist their own rotational speeds. Yet, for all its crucial role, dark matter does not interact with electromagnetic forces. It neither emits nor absorbs light. As such, it can only be detected through its gravitational effects. Dark energy, on the other hand, is even more perplexing. It represents the unseen force accelerating the expansion of the universe, a discovery that upended prior cosmological models. While dark matter serves to bind the universe together, dark energy works in the opposite direction, pushing it apart. Together, these forces form an intricate cosmic dance, one that shapes the evolution of the universe. The universe's origin, often described as the Big Bang, presents a mind-boggling scenario where the laws of physics, as we understand them today, were both profoundly relevant and uniquely challenged. Around 13.8 billion years ago, the universe was compressed into a singularity, a point of infinite density and temperature. During this infinitesimally brief moment, known as the Planck epoch, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single, undifferentiated force. However, the conditions were so extreme that our current understanding of physics, including both general relativity and quantum mechanics, becomes incomplete, if not outright divergent. As the universe began to expand and cool, it transitioned through various epochs, each marked by the gradual differentiation of the fundamental forces. Within the first fraction of a second, the fundamental forces separated, and the quark-gluon plasma, a state of matter where quarks and gluons roamed freely, eventually condensed into protons and neutrons. As the universe continued to cool over the next thousands of years, atoms began to form, leading to the creation of the first simple elements such as hydrogen and helium. These early moments in the universe's history were crucial, as they set the fundamental properties that would govern everything that followed. From the motion of galaxies to the life cycle of stars, and even the behavior of particles in laboratories today, the laws of physics that emerged during this time continue to shape the universe. The astonishing transitions in the universe's evolution reveal how the laws of physics have not only governed but also emerged from the chaotic dance of creation. General relativity, formulated by Albert Einstein in 1915, completely revolutionized our understanding of gravity and the very fabric of space-time. It gave us a profound new perspective on the universe's origin. Unlike the earlier Newtonian view, which treated gravity simply as a force between two masses, general relativity painted a more intricate picture. It portrayed gravity as the curvature of space-time itself, a phenomenon caused by the presence of mass and energy. This radical shift in thinking allowed us to understand the vast, sweeping motions of cosmic structures, from galaxies to stars and planets, even how light itself navigates the curved contours of space-time. Within the context of the universe's origin, general relativity plays a pivotal role. It provides the mathematical framework for the Big Bang theory, suggesting that the universe had a singular, incredibly dense and hot starting point, a singularity. This singularity, existing some 13.8 billion years ago, marks the birth of space-time itself. Through the lens of Einstein's equations, we can trace the history of the cosmos back to this moment, where every particle, every bit of energy, and all of the mass we know today was contained within this incredibly small and concentrated point. Solutions to these equations, like the celebrated Friedmann-Lemaitre-Robertson-Walker FLRW metric, allow us to understand how the universe expanded and evolved over time. One of the most fascinating predictions of general relativity is the existence of cosmic microwave background radiation, remnants of heat from the Big Bang. This faint, persistent radiation has been detected and measured, providing compelling evidence that the universe did indeed begin from such a hot and dense state. Thus, general relativity not only aids in conceptualizing the universe's beginnings, but it continues to be an indispensable tool in our exploration of the vast cosmic expanse and its ongoing evolution. On the other hand, quantum mechanics and cosmology may seem to occupy vastly different realms. Quantum mechanics governs the world of particles and the microscopic scale, while cosmology seeks to unravel the mysteries of the entire universe. Yet these fields intersect profoundly at the boundaries of our knowledge. Quantum mechanics, with its strange principles of superposition, entanglement, and uncertainty, explains the behavior of particles at the smallest levels. Cosmology, by contrast, studies the grand evolution of the universe, its birth, expansion, and structure on the largest scales. This intersection becomes especially important when considering the universe's earliest moments, known as the Planck epoch. This minuscule period of time, lasting only a fraction of a second, was dominated by quantum effects on a macroscopic scale. In the aftermath of the Big Bang, the universe was so compact and hot that minute fluctuations in energy levels played a significant role in shaping its early development. These tiny quantum fluctuations were amplified during the period known as cosmic inflation, a rapid and exponential expansion that set the stage for the large-scale structures we see today, such as galaxies and clusters of galaxies. As we delve deeper into these foundational intersections, theories such as string theory and quantum gravity strive to unify general relativity with quantum mechanics. These theories aim to provide a comprehensive understanding of the earliest moments of the universe. Concepts like the multiverse emerge from these efforts, suggesting that our universe might be just one of many, each governed by its own set of physical laws and constants. By probing these intersections, scientists hope to uncover a unified theory that seamlessly integrates the quantum and cosmic scales, offering a more profound understanding of the universe, from its tiniest particles to its grandest phenomena. The pursuit of this knowledge remains one of the most exciting and challenging endeavors in modern physics. Singularities, regions in space-time where the gravitational field becomes infinitely strong, represent some of the most puzzling aspects of our universe. These points are characterized by extreme densities and infinitesimally small volumes, causing mathematical descriptions of space-time to break down. Singularities are most famously associated with black holes, mysterious cosmic anomalies where the gravitational pull is so intense that not even light can escape, Within these black holes, the core collapses into a point-like singularity, often hidden behind an event horizon, making it impossible to observe directly. When we turn our attention to the universe's beginning, singularities take on an even more monumental role. According to the Big Bang Theory, the universe itself originated from an initial singularity around 13.8 billion years ago. This primal singularity is thought to have contained all of the universe's mass and energy in an infinitely small point, a state so extreme that our current understanding of physics, especially general relativity, cannot fully describe it. Quantum mechanics, which governs the behavior of the smallest particles, also struggles to provide a complete picture of this moment. Thus, singularities serve as a reminder of the limitations of our existing theories and drive the search for new unifying theories. They highlight the need for a framework that can reconcile quantum mechanics with general relativity, potentially in the form of quantum gravity. By studying these singularities, scientists aim to unlock the secrets of the universe's origins, hoping to reveal the fundamental laws that govern the first moments of existence and continue to shape the cosmos's vast and intricate evolution. Modeling the universe's beginning requires a robust set of mathematical tools, drawn primarily from general relativity and quantum mechanics, each contributing a unique framework. In general relativity, Einstein's field equations are foundational. These equations describe the curvature of spacetime in the presence of mass and energy, and are essential for constructing models of the universe's early state, where extreme densities and gravitational forces dominated. Solutions to these equations, such as the Friedmann-Lemaitre-Robertson-Walker metric, describe a universe that begins from a singularity and expands over time, helping us to understand the dynamics of cosmic growth. On the quantum mechanical side, the tools are different but equally powerful. Wave functions, which provide probabilistic descriptions of particles, form the core of quantum theory. Quantum field theory extends these principles to fields, providing a framework for understanding particle behavior under the extreme conditions of the early universe. Techniques like renormalization, which helps deal with the infinities that arise in quantum calculations, allow for more manageable and meaningful results. Together, these tools, from general relativity and quantum mechanics, allow us to piece together a picture of the universe's earliest moments, striving toward a unified understanding of the cosmos, its past, present, and future. Cosmology has entered a new era, one shaped by the power of sophisticated algorithms and computational simulations that allow us to model the complex and often elusive interactions and evolution of the universe. These advanced techniques serve as a virtual laboratory, providing cosmologists with the ability to simulate the dynamic processes that have shaped the cosmos over its vast history. By employing methods such as large-scale simulations and n-body simulations, scientists can explore the intricacies of the universe's birth and ongoing transformation. These mathematical tools offer a lens through which to view the unimaginable events that took place during the early universe, offering insights into phenomena like cosmic inflation, the rapid expansion that smoothed and stretched the minute quantum fluctuations that once existed, ultimately giving rise to the large-scale structures of the universe we observe today. As computational methods continue to evolve, so too does our understanding of the cosmos, bringing us ever closer to uncovering the mysteries that lie at the heart of its origin. Physicists now harness the immense power of computer simulations to study the universe's birth. By creating highly detailed models that reflect the conditions and processes thought to have occurred in the universe's infancy, these simulations are rooted in both general relativity and quantum mechanics, integrated with advanced computational algorithms that can manage vast quantities of data and complex calculations. One of the key applications of these simulations is the study of cosmic inflation, a period of rapid expansion occurring mere fractions of a second after the Big Bang. Using initial conditions derived from theoretical models such as the early universe's energy density and the properties of quantum fields, researchers can simulate the inflationary phase to observe how tiny quantum fluctuations were stretched to macroscopic sizes. These simulations not only deepen our understanding of how the universe evolved, but also illuminate how those minute fluctuations were eventually responsible for the formation of galaxies and galaxy clusters. Furthermore, computational simulations play a crucial role in modeling the formation and development of cosmic structures. By employing n-body simulations, which track the gravitational interactions between a large number of particles, scientists can reconstruct the assembly of dark matter halos and the subsequent formation of galaxies. These simulations often run on some of the most powerful supercomputers available, enabling them to produce high-resolution results that offer intricate insights into the processes that govern cosmic development. By comparing these simulated results with observational data, such as the cosmic microwave background radiation or the distribution of galaxies, physicists can refine their models and deepen their understanding of the universe's evolution. These computational studies serve as invaluable tools, offering a virtual space where hypotheses can be tested and theories validated, helping to build a more refined and comprehensive understanding of the universe's origin and its constantly shifting, ever-evolving nature. Several key astronomical observations provide robust evidence supporting current theories about the universe's origin, particularly the Big Bang theory. These observations, which span vast timescales and encompass a wide range of phenomena, offer converging lines of evidence that help to assemble the cosmic story. One of the most significant pieces of evidence comes from the faint glow of microwave radiation that pervades the entire universe, known as the cosmic microwave background, CMB. This afterglow is the residual thermal radiation from the time when the universe had cooled enough for photons to decouple from matter, approximately 380,000 years after the Big Bang. The uniformity and slight anisotropies observed in the CMB provide critical information about the early universe's conditions, lending strong support to the idea that the universe originated from a hot, dense state and then expanded. Another pivotal observation comes from the redshift of distant galaxies, a phenomenon first noted by Edwin Hubble in the 1920s. Hubble discovered that galaxies are receding from us at speeds that are proportional to their distance, a discovery encapsulated in what is now known as Hubble's law. This galactic redshift is an unmistakable sign that the universe is expanding, which serves as one of the cornerstones of the Big Bang theory. It also implies that galaxies were once much closer together, pointing to a singularity, or a point of origin, from which the universe's expansion began. In addition to these key observations, the abundance of light elements, such as hydrogen, helium, and traces of lithium, offers further confirmation of the Big Bang theory. These elements were predicted to form during the early minutes of the universe's existence through a process called Big Bang nucleosynthesis, which describes the formation of the universe's first elements under extreme temperatures and densities. The observed concentrations of these elements align closely with the predictions made by this theory, further validating the concept that the early universe was hot and dense enough to give rise to these light elements. Together with other observations, such as the large-scale distribution of galaxies and the effects of gravitational lensing, these findings help to strengthen the Big Bang theory. They offer a coherent and comprehensive picture of the universe's origins, bridging theoretical models with empirical data and significantly enhancing our understanding of cosmic evolution. The development of cutting-edge telescopes and satellites has been instrumental in revolutionizing our understanding of the early universe. These sophisticated instruments extend our vision far beyond the limitations of the naked eye, capturing light from some of the most distant and ancient objects, many of which formed shortly after the Big Bang. Space-based observatories, such as the Hubble Space Telescope and the more recent James Webb Space Telescope, play a pivotal role in this endeavor. Positioned above Earth's atmosphere, these telescopes avoid the distortions caused by the atmosphere, allowing them to observe a wider range of wavelengths, from ultraviolet to infrared. The Hubble Space Telescope, in particular, has provided deep field images revealing thousands of galaxies at various stages of evolution, some of which date back over 13 billion years. These images provide a unique opportunity for scientists to study the formation and development of galaxies, stars, and other cosmic structures during the universe's formative years. In the realms of microwave and radio astronomy, satellites like the Cosmic Background Explorer, CE, the Wilkinson Microwave Anisotropy Probe, WMAP, and and the Planck satellite have been essential in mapping the cosmic microwave background radiation. These missions have provided precise measurements of the tiny temperature fluctuations in the CMB, offering a snapshot of the universe just 380,000 years after the Big Bang. The detailed maps generated by these satellites provide crucial insights into the early universe's conditions, the nature of dark matter and dark energy, and the overall geometry and expansion rate of the cosmos. Through these groundbreaking efforts, telescopes and satellites have greatly expanded our knowledge of the universe's origins, providing us with the tools needed to peer into the distant past and understand the early stages of the cosmos. In the vast and intricate field of cosmology, scientists are constantly pushing the boundaries of our understanding, exploring the earliest moments of the universe and uncovering the forces and phenomena that shaped its evolution. Instruments like the Large Hadron Collider, LHC, are crucial to this exploration. By accelerating particles to nearly the speed of light and colliding them at immense energies, the LHC replicates conditions that were present just moments after the Big Bang. These collisions provide a direct look at the fundamental particles and forces that governed the universe's infancy. The LHC's experiments have led to groundbreaking discoveries, including the confirmation of the Higgs boson in 2012, which elucidated the mechanism by which particles acquire mass, shedding light on the very origins of matter itself. But the LHC is not the only instrument contributing to our understanding. Gravitational wave observatories such as LIGO and Virgo are also invaluable in probing the cosmos. These observatories detect the ripples in spacetime created by cataclysmic events like black hole mergers. Although these events occurred far in the past, the waves they generate still reach us, offering indirect evidence of processes that took place in the early universe. By studying gravitational waves, scientists are able to peer into the deepest recesses of spacetime, revealing phenomena that traditional telescopes cannot detect. Telescopes and satellites are also instrumental in this quest for knowledge. These devices act as time machines, allowing astronomers to observe distant galaxies and other cosmic phenomena as they were billions of years ago. This allows us to study the universe's past, its formation, and its evolution. The Hubble Space Telescope, for instance, has provided us with breathtaking deep-field observations of galaxies dating back to the universe's infancy. These galaxies, often smaller and less structured than the ones we see today, provide a glimpse into the early stages of galaxy formation. They were often engaged in frequent mergers, interactions that played a vital role in their evolution into the more massive, structured galaxies we observe today. The study of quasars, extremely luminous objects powered by supermassive black holes at the centers of young galaxies, further enriches our understanding of the early universe. These black holes consume matter at prodigious rates, emitting vast amounts of radiation across multiple wavelengths. Observing quasars allows scientists to study the formation and growth of these supermassive black holes, while the light they emit passes through intervening clouds of gas, offering insights into the composition and evolution of the intergalactic medium. Furthermore, quasars serve as beacons for mapping the large-scale structure of the universe, helping scientists to map the vast cosmic web and observe how matter is distributed across the universe. Moreover, the study of quasars provides a window into the epoch of reionization, a period when the universe's initially neutral hydrogen gas was ionized by the first stars and galaxies. This critical phase marks the transition from a dark, opaque universe to one filled with the light of the first cosmic structures. By examining quasars and distant galaxies, astronomers are able to trace the formation of the universe's early structure and further understand the processes that have led to the cosmos we know today. In addition to these observations, the study of the cosmic microwave background, CMB, radiation, is pivotal in understanding the universe's beginnings. The CMB is the faint afterglow of the Big Bang, a nearly uniform radiation field that permeates the entire universe. It provides a snapshot of the cosmos as it existed around 380,000 years after the Big Bang, offering a glimpse into the universe's earliest moments. Detecting and studying the CMB requires sophisticated instruments that can isolate microwave signals from other sources of interference, including those from our own galaxy. Several missions have significantly advanced our understanding of the CMB. The Cosmic Background Explorer, COBE-E, launched in 1989, was one of the first to provide detailed measurements of the CMB, confirming its uniformity and detecting slight temperature fluctuations or anisotropies that hint at the density variations which led to the formation of galaxies. This work was further refined by the Wilkinson Microwave Anisotropy Probe, WMEP, in 2001, which provided higher resolution maps of the CMB, helping to refine estimates of the universe's age, composition, and curvature. The most recent and sophisticated mission in this field is the Planck satellite, launched by the European Space Agency in 2009. Planck provided the most detailed measurements of the CMB to date, capturing variations in temperature and polarization across the sky with unprecedented resolution. These measurements are crucial because they help scientists understand the fundamental properties of the universe, including its rate of expansion and the composition of matter and energy. By studying the CMB, cosmologists can learn about the initial conditions that led to the formation of galaxies and the large-scale structures that make up the universe today. Beyond space-based observatories, ground-based and balloon-borne experiments are also essential for studying the CMB. Instruments such as the Atacama Cosmology Telescope ACT and the South Pole Telescope SPT observe the CMB from high-altitude locations, where the atmosphere is thinner and interference is reduced. Balloon experiments like Boomerang and Archeops have also provided crucial data, capturing detailed measurements of the CMB from the upper atmosphere. These diverse efforts help cosmologists piece together a comprehensive understanding of the universe's infancy. The detailed analysis of CMB data is a complex process involving intricate algorithms and models to interpret the temperature and polarization patterns observed across the sky. This analysis provides key insights into the universe's early history, such as the rate of expansion, the density of matter and energy, and the conditions that led to the formation of galaxies. Together, these observations from various instruments and missions have provided substantial empirical evidence supporting the Big Bang theory, further enhancing our understanding of the universe's evolution. Particle accelerators like the LHC also play an integral role in understanding the early universe by replicating the extreme conditions that existed immediately after the Big Bang. The LHC, located at CERN near Geneva, is the world's largest and most powerful particle accelerator, capable of achieving collision energies up to 13 tera-electron volts. By smashing protons and heavy ions together at these incredible energies, the LHC creates a miniaturized version of the high-energy conditions that existed in the universe's infancy. This allows scientists to probe the fundamental forces and particles that govern the cosmos. One of the most significant achievements of the LHC was the discovery of the Higgs boson in 2012. This particle confirmed the mechanism by which elementary particles acquire mass and helped refine the standard model of particle physics, a framework that describes the fundamental particles and interactions in the universe. The study of the Higgs boson and other particles created in the LHC's collisions provides critical insights into the nature of the early universe, helping to unlock the mysteries of matter, energy, and the forces that govern the cosmos. In conclusion, the tools and technologies employed by scientists today, from particle accelerators to gravitational wave detectors to advanced space telescopes, are helping to unravel the deepest mysteries of the universe. These instruments allow us to peer back in time, studying the formation of galaxies, the birth of supermassive black holes, and the conditions that shape the cosmos. Each discovery contributes to a larger picture of how the universe evolved from the moment of the Big Bang to the complex, ever-expanding cosmos we observe today. These ongoing efforts are expanding our knowledge of fundamental physics, cosmology, and astrophysics, helping us understand the universe at its most profound level. These experiments provide indirect but invaluable evidence, shedding light on the conditions and processes that unfolded during the universe's infancy. A prime example is the study of quark-gluon plasma, a unique state of matter that existed mere microseconds after the Big Bang. This plasma is made accessible to researchers through heavy ion collisions in particle accelerators. By recreating the extreme conditions present in the early universe, scientists can study the behavior of the strong nuclear force. the very force that binds quarks together within protons and neutrons. Such studies help us understand the fundamental interactions that shape matter in its earliest form. Moreover, particle accelerators are not limited to investigating the particles we already know. They also provide an experimental platform for exploring the elusive realms of new physics that lie beyond the standard model. Hypotheses such as supersymmetry, the existence of extra dimensions, and candidates for dark matter are all subjects of active investigation. Discovering or ruling out these theories could revolutionize our understanding of the universe's formation and the very laws of nature that govern it. In parallel, particle accelerators contribute vital data that refine cosmological models, helping to support experiments in particle astrophysics, including those that investigate neutrinos, particles with profound implications for the universe's overall mass and energy balance. In essence, particle accelerators have become indispensable tools in modern physics. They allow us to simulate the high-energy environments of the early universe and perform deep investigations into the fundamental particles and forces that govern the cosmos. The discoveries born of these experiments not only validate and refine existing theories, but also open new doors to understanding the profound mysteries of the universe's origins and its fundamental nature. However, studying the universe's origins is far from straightforward. It presents monumental challenges, both technological and conceptual. The primary difficulty lies in the vast scale of time and space involved. The events that transpired nearly 8 billion years ago are so distant, both in terms of time and space, that observing and interpreting signals from that era requires technology that pushes the very limits of what we currently possess. Instruments like the James Webb Space Telescope have been meticulously designed to capture the faint light from the early universe, but even such sophisticated devices have their limits. The farther back in time we look, the fainter and more red-shifted the signals become, demanding instruments with even greater sensitivity and new methods of data analysis. Moreover, our understanding of the fundamental laws of physics presents its own set of challenges. The conditions at the dawn of the universe were extreme, involving energy and densities far beyond what we can replicate in laboratories on Earth. Theoretical models, such as those developed through quantum mechanics and general relativity, often conflict when applied to these extreme conditions. This discord leads to incomplete or contradictory descriptions of the early universe, which is why physicists are still on the hunt for a unifying theory, one that can reconcile these differences and explain the most fundamental aspects of the cosmos. Achieving this is one of the most formidable challenges in modern science. Even concepts like dark matter and dark energy, which make up about 85% of the universe's mass, and energy content, remain enigmatic. Despite being integral to the universe's structure and evolution, we still do not fully understand what they are or how they interact with ordinary matter. Investigating these mysterious substances holds the potential to unlock key aspects of the universe's early development. How did dark matter influence the formation of cosmic structures in the infancy of the universe? What role does dark energy play in the accelerated expansion of the universe, which began billions of years after the Big Bang? These fundamental questions challenge us to delve deeper into the unseen, largely unknown facets of the cosmos. Additionally, the quest to unify general relativity with quantum mechanics, a search for a theory of everything, remains an unfulfilled goal. Both theories are cornerstones of modern physics, but under the extreme conditions of the early universe, they become incompatible. A unified theory could offer crucial insights into the very beginning of the Big Bang, possibly explaining the nature of space and time itself. Each of these questions represents an uncharted frontier in our understanding of the universe, a reminder that the origins of the cosmos are not only a scientific puzzle, but a profound mystery that continues to inspire human curiosity and ingenuity. Studying the conditions preceding the Big Bang poses an array of formidable challenges, largely due to the limitations inherent in our current scientific theories and observational tools. One of the most significant hurdles is the concept of before the Big Bang. According to general relativity, time and space, as we know them, were created with the Big Bang itself. This implies that any event or condition that may have existed before the Big Bang lies outside the framework of conventional time, making it inherently difficult, if not impossible, to study within our current scientific paradigms. Our understanding of causality and time is deeply rooted in the structure of space-time, as described by relativity. Yet, this theory doesn't provide a framework for events that occur outside of this continuum. As a result, any attempt to study the before becomes speculative at best. This paradoxical challenge is a direct consequence of the fact that, from a theoretical standpoint, the laws of physics themselves break down under such extreme conditions, leaving us with an incomplete picture of what may have preceded the birth of the universe. Such questions continue to push the boundaries of our understanding, forcing us to reconsider fundamental assumptions about time, space, and the origins of everything we know. As researchers strive to answer these mysteries, they are not only reshaping the field of cosmology, but are also expanding the horizons of human knowledge itself. The journey to unlock the secrets of the universe's beginning is one that promises to challenge the very fabric of our scientific and philosophical understanding for years to come. The realm preceding the Big Bang is shrouded in mystery, with theories suggesting it was a place of unimaginable density and temperature. It was an environment where the fundamental laws of physics, as we understand them, particularly general relativity and quantum mechanics, simply ceased to function. These two cornerstone theories of modern physics are essential in their own realms. General relativity governs the large-scale structure of space-time, while quantum mechanics describes the behavior of subatomic particles. However, these two theories are notoriously incompatible under the extreme conditions believed to have existed before the Big Bang. This discrepancy makes it clear that a new theory, one that seamlessly merges the ideas of both general relativity and quantum mechanics, is necessary to accurately describe the conditions before the universe's birth. Until such a theory is developed and validated, our understanding of this period remains fragmented and largely speculative. On the observational front, our primary tool for studying the universe's early days is electromagnetic radiation. However, this too has its limitations. The farthest back we can observe directly is the cosmic microwave background radiation, CMBR, which represents the state of the universe approximately 380,000 years after the Big Bang. This is when photons decoupled from matter, allowing light to travel freely through space. Before this epoch, the universe was opaque to electromagnetic radiation, making direct observations impossible. As a result, we are left with no choice but to infer the conditions that existed before the CMBR through theoretical models and indirect measurements. These include emerging fields such as the detection of gravitational waves or the study of particle interactions, both of which continue to develop. Yet these indirect methods can only provide glimpses into a much more distant and mysterious past. Thus, the study of the conditions before the Big Bang is an intensely challenging yet equally fascinating frontier in cosmology. The twin obstacles of theoretical limitations and observational constraints push scientists to continually refine their models and develop new technologies. These challenges are not deterrents. Rather, they drive the relentless quest to unlock one of the most profound mysteries of our existence, the origin of the universe itself. The pursuit of understanding the universe's origin is further hampered by significant technological limitations. One of the most pressing challenges is the sensitivity and resolution of our observational instruments. Telescopes such as the Hubble Space Telescope, along with the more advanced James Webb Space Telescope, have provided breathtaking images and valuable data from across the cosmos. However, even these state-of-the-art devices are limited in their ability to detect extremely faint signals from the early universe. As we look further back in time, the signals we receive become progressively fainter and more redshifted, requiring even more sensitive instruments to capture these elusive photons. Despite the remarkable achievements of current technology, much of the universe's history, particularly the moments immediately following the Big Bang and the time before it, remains out of reach. In addition to observational challenges, there are substantial limitations in our ability to replicate and study the conditions of the early universe in terrestrial laboratories. While Particle accelerators like the Large Hadron Collider, LHC, can recreate the conditions that existed mere fractions of a second after the Big Bang. By accelerating particles to near light speed and colliding them, they fall short of simulating the extreme conditions near the singularity from which the Big Bang emerged. The energy scales involved in these experiments are still far below those believed to have been present during the universe's birth, meaning our theoretical models remain largely untested in this crucial domain. Another critical technological barrier concerns the detection and study of dark matter and dark energy. Together, these two mysterious substances account for approximately 85% of the universe's mass energy content. Despite extensive efforts, current detectors for dark matter, often elaborate underground experiments shielded from cosmic rays, have yet to definitively capture a single dark matter particle. Similarly, dark energy, which was inferred from the accelerated expansion of the universe, remains enigmatic in terms of its properties and origins. These unknowns continue to constrain our overall understanding of the universe's origin, as both dark matter and dark energy likely played pivotal roles in shaping the cosmos. Moreover, data processing and computational limitations further complicate our quest for understanding. Analyzing the massive datasets generated by observatories and experiments demands immense computational power and sophisticated algorithms. Although significant progress has been made in this area, the ever-increasing volume and complexity of data necessitate continual advancements in computational technologies. Quantum computing, for instance, may one day provide the computational power required to model early universe conditions with greater accuracy. Together, these technological limitations form a substantial barrier to fully comprehending the origins of the universe. Yet, rather than hindering progress, they serve as catalysts for innovation. These constraints continuously drive the improvement of scientific instruments and methodologies. The ongoing pursuit of overcoming these obstacles remains one of the central inspirations of the scientific community, pushing forward our understanding of the cosmos. One of the most perplexing and philosophically intriguing concepts in cosmology is the idea of nothing. In everyday language, nothing refers to the absence of everything. No matter, no energy, no space, and no time. A true void. However, when scientists approach this concept, particularly in the context of the universe's origin, it takes on a more nuanced and profound meaning. According to quantum mechanics, even a perfect vacuum, what we might consider nothing, is not truly empty. Due to the uncertainty principle, fluctuations occur at the quantum level, with particle-antiparticle pairs constantly forming and annihilating almost instantaneously. This phenomenon suggests that nothing is not a static void, but rather an active, dynamic state. These quantum fluctuations offer a fascinating possibility that something could indeed emerge from nothing. For example, some cosmological models propose that the universe might have arisen from a quantum vacuum fluctuation, an unstable, fleeting imbalance that ultimately gave rise to everything we observe. This model challenges our classical intuitions about the origin of the universe, proposing that the seeds of everything we know today could have come from an ephemeral state of nothingness. It's a concept that continues to spark debates and fuel further investigation, as we seek to understand the very nature of existence itself. The concept of nothing is not merely an abstract philosophical question. It has profound implications in the realms of physics and cosmology, where it intersects with some of the most intriguing theories about the origins of the universe and the fundamental nature of reality. This idea extends beyond the boundaries of classical thinking, presenting a paradox that challenges our understanding of existence itself. In the context of the multiverse theory, nothing takes on a surprising role. Imagine our universe as just one of many, each emerging from different vacuums or distinct phases within a vast and overarching multiverse. Here, what we perceive as nothing might not be truly devoid of substance. Rather, it could be part of a continuously fluctuating, multidimensional space that is beyond our comprehension. In these models, the birth of a universe could be viewed as a transition from a state of nothingness in one dimension or construct to the emergence of something, governed by entirely different sets of physical laws. This radical shift in thinking presents a view of the universe's birth as not just a creation event, but as a movement from one state of being to another, a transformation governed by principles that we have yet to fully grasp. Cosmologists have further explored this concept through the framework of general relativity and the fabric of space-time. The theory of the inflating universe, one of the most widely accepted models in cosmology, suggests that our universe underwent a rapid and expansive growth from an incredibly tiny, hot, and dense singularity. According to this theory, the concept of nothing can be envisioned as a state that precedes the very dimensions that define our current reality. In this state, there would be no space, no time, nothing at all in the conventional sense. The transition from this absolute nothingness to our ever-expanding universe might seem counterintuitive at first glance. Yet, it aligns with certain interpretations of how physical laws might operate in realms outside our known space-time continuum, where the boundaries of existence are not confined to what we can observe or measure. Addressing the idea of nothing isn't solely an academic exercise. It involves a concerted, interdisciplinary effort that blends quantum mechanics, general relativity, and deep philosophical inquiry. Scientists are not just debating semantics. They are pushing the frontiers of knowledge and technology in an attempt to unlock the mysteries of existence itself. This pursuit serves as a critical frontier in our quest to understand not just the origins of the universe, but the very essence of what it means to be. The implications of unraveling the mysteries of the universe's origins extend far beyond the walls of theoretical physics. These discoveries have far-reaching effects on a variety of scientific disciplines, offering new insights that drive innovation in unexpected ways. In physics, for instance, cosmological discoveries help refine our understanding of the fundamental particles and forces that make up the universe. Conditions during the universe's earliest moments serve as a kind of natural laboratory for testing the limits of particle physics. This includes gaining a deeper understanding of phenomena like the behavior of the Higgs boson and the mysterious properties of neutrinos. These insights not only push the boundaries of scientific thought, but also translate into practical advancements. Technologies such as medical imaging devices and particle accelerators owe their development in part to these cosmological explorations. Astronomy and astrophysics, too, are profoundly impacted by our quest to understand the universe's origins. The study of cosmic phenomena like the cosmic microwave background radiation offers critical clues about the universe's early density fluctuations, which eventually led to the formation of galaxies and clusters of stars. This knowledge enriches our understanding of the vast structures that make up the universe and also aids in the search for potentially habitable exoplanets. It also opens the door to the exploration of extraterrestrial life, an area that remains one of the most tantalizing questions of modern science. The intersection of cosmology with chemistry further illustrates how the study of the universe's birth impacts our understanding of the natural world. The elements that make up everything we see today, every star, planet, and organism, were formed through nuclear synthesis in the moments following the Big Bang, as well as in the cores of stars throughout cosmic history. Chemists study these processes to better understand the building blocks of matter, influencing the development of new materials and enhancing our understanding of biochemical processes essential for life itself. Beyond these natural sciences, the principles derived from cosmological research have applications in engineering as well. The techniques used to measure vast cosmic distances and map the structure of the universe, such as the Doppler effect and spectroscopy, have practical implications in the development of advanced navigation systems. Additionally, they play a critical role in improving precision in engineering disciplines, from satellite technology to deep space exploration. The technologies developed to observe distant cosmic events often lead to innovations that ripple across industries, enhancing computational methods, data processing, and imaging technologies. On a more abstract level, the study of the universe's origins has deep philosophical and existential implications. It shapes our understanding of humanity's place in the cosmos, influencing not just scientific inquiry, but also ethical and societal considerations. This broader perspective has profound effects on how we view our responsibilities as stewards of Earth as well as our role in the wider universe. It prompts questions about sustainability, the future of human civilization, and how we navigate our existence within a vast, interconnected universe. In conclusion, the pursuit of understanding the origins of the universe is not a solitary endeavor confined to any one field. It is a dynamic catalyst that drives progress and innovation across a multitude of scientific disciplines. It challenges our conventional frameworks, pushing us to rethink time, space, and existence itself. The Big Bang Theory, for instance, offers a revolutionary perspective. Time and space did not exist before the singularity. Instead, they themselves were born from this explosive event, fundamentally altering our understanding of how the universe came into being. In this view, time and space are not static entities, but are instead dynamic, evolving constructs. According to Einstein's theory of general relativity, time is not simply an unchanging backdrop to the events of the universe. Rather, it bends and flows in response to mass and energy. This is most dramatically illustrated by the concept of space-time curvature, where massive objects like stars and planets distort the space-time fabric around them. The phenomenon of gravitational time dilation, where time behaves differently near a black hole, underscores the malleable nature of both time and space, further challenging our everyday intuitions and extending the boundaries of our understanding of the cosmos. In the earliest moments of the universe, conditions were so extreme that the laws of physics as we know them could no longer be applied. Approaching the singularity, this point where time and space as we understand them cease to exist, forces us to rethink our fundamental assumptions about the nature of time itself. This period, often called the Planck epoch, takes us back to an era when space-time was governed by forces beyond current comprehension. At such scales, time might not unfold as a smooth, continuous line, but rather might be quantized, divided into discrete intervals. This idea, which is still at the frontier of theoretical research, challenges our very understanding of time, suggesting that it could behave in ways we have yet to grasp, waiting for a future theory of quantum gravity to offer a unified framework that combines the microscopic world of quantum mechanics with the macroscopic world of general relativity. Theories like loop quantum gravity or the notion of discrete time continue to evolve, pushing the boundaries of what we know about time's role in the birth of the universe. These investigations are key to understanding how time itself may have emerged from the chaos of the early cosmos. But beyond time, the universe's expansion itself provides another vital clue to the intricate dance between space and time. Dark energy, a mysterious and poorly understood force, drives the acceleration of this expansion, suggesting that the very fabric of space is stretching. This stretching causes galaxies to drift away from each other, marking the universe's ongoing evolution. As the space between galaxies expands, light traveling through it is stretched as well, resulting in the phenomenon of redshift. This stretching of space means that our traditional concepts of distance and time must be rethought. Far from being an inert backdrop, space is an active participant in the cosmic drama. It shapes the universe's past and continues to influence its future, driving the distances between galaxies ever farther apart. This cosmic expansion reveals that time and space are not immutable. Instead, they are fluid, intertwined elements that have evolved alongside the universe itself, and this dynamic relationship remains a source of scientific and philosophical exploration. Time, once perceived as a linear and unchanging continuum, is now seen as a malleable force, constantly shaped by the forces acting upon it. This evolving understanding of time and space forces us to confront the very nature of existence. The realization that both time and space had a beginning at the moment of the Big Bang forces a radical shift in how we perceive reality. We are conditioned to think of time as an unbroken flow, stretching endlessly in both directions. Yet, the idea that time itself had a starting point nearly 13.8 billion years ago suggests that our everyday intuitions about time are fundamentally flawed. Instead of being an unchanging constant, time is deeply interconnected with the fabric of space and matter, and it has evolved alongside the universe. This realization compels us to reconsider our entire conceptual framework for understanding reality. The implications of quantum mechanics, which govern the behavior of particles at the smallest scales, further deepen the mystery. Quantum phenomena like superposition and entanglement show that particles can exist in multiple states at once and can instantaneously affect one another across vast distances. These behaviors challenge our traditional notions of causality and locality, opening new philosophical debates about the very nature of reality. At the quantum level, the universe appears to operate on probabilities rather than certainties, suggesting that our macroscopic reality, what we observe on a daily basis, emerges from underlying processes that are far more interconnected and probabilistic than we might ever imagine. Another monumental discovery, dark matter and dark energy, adds yet another layer of complexity to our understanding of the cosmos. These invisible components make up approximately 85% of the universe's mass-energy content, yet they remain largely mysterious. Our current scientific models built on observable phenomena are woefully incomplete. These hidden forces suggest that what we see, the stars, planets, and galaxies, is just a tiny fraction of what truly exists. Grasping the nature of dark matter and dark energy could forever alter our understanding of cosmic evolution, from the formation of galaxies to the ultimate fate of the universe itself. The study of the universe's origins doesn't just have scientific implications. It also forces us to grapple with profound existential questions. If the universe has a beginning, an evolution, and possibly even a finite future, where does humanity fit within this grand cosmic narrative? Are we a part of a vast and purposeful design, or merely the result of chance and natural processes in an indifferent universe? These questions, prompted by the study of the cosmos, have a profound influence on our worldview, prompting philosophical, theological, and ethical discussions that extend far beyond the realm of science. Ultimately, the study of the universe's beginning is not just a scientific endeavor, but a philosophical journey, one that reshapes our understanding of existence itself. It challenges our core assumptions, pushes the boundaries of what we consider possible, and offers profound insights into the nature of reality. As we venture further into the unknown, we are not just expanding our knowledge of the cosmos, we are redefining the very parameters by which we understand the world around us. Looking into the future of the universe, the scenarios become even more intriguing. One of the most compelling is the role of dark energy, which is responsible for the accelerated expansion of the cosmos. If dark energy remains constant, the universe will continue to expand indefinitely, leading to what is known as the Big Freeze or heat death. In this scenario, galaxies will drift farther and farther apart, stars will burn out, and the universe will eventually become a cold, dark, and lifeless void. Over vast timescales, even black holes would evaporate via Hawking radiation, leaving behind only a dilute soup of particles in an ever-expanding emptiness. However, a more dramatic scenario known as the Big Rip remains a theoretical possibility. If dark energy becomes stronger over time, it could eventually overpower all other forces, tearing apart galaxies, stars, planets, and even the fabric of space-time itself. While less likely according to current observations, the Big Rip remains an intriguing topic of study among cosmologists. On the other hand, there is a possibility, though it too remains speculative, that the universe could eventually contract in a scenario known as the Big Crunch. If the universe's density is high enough, gravitational forces could eventually slow and reverse the expansion, causing everything to collapse back in on itself. In this scenario, galaxies would collide, stars would burn up in cataclysmic bursts, and temperatures would soar to unimaginable heights as the universe reverts to a dense, hot singularity. The fate of the universe may still be uncertain, but as we study these possibilities, we are constantly reminded of how much there is left to discover. Whether we are pondering the earliest moments of the Big Bang, investigating the strange behaviors of quantum particles, or contemplating the future end of the cosmos, the journey continues. And with it comes an ever-deepening sense of wonder and awe about the vast, dynamic universe we are all a part of. The ultimate fate of the universe is one of the most profound mysteries that has captivated both scientific and philosophical minds for centuries. At the heart of this cosmic enigma lies the possibility that the universe could one day collapse back into a hot, dense state. This collapse, often referred to as the Big Crunch, could recreate the conditions akin to those at the very birth of the universe, potentially leading to a new era of cosmic rebirth. In some speculative theories, this collapse may not merely mark an end, but could trigger another Big Bang, giving rise to an eternal cycle of birth, expansion, contraction, and rebirth. This cyclical model of the universe suggests that the cosmos may not have a definitive beginning or end, but instead undergoes an endless process of creation and destruction, with each cycle potentially bringing forth a new universe in a sequence of infinite beginnings. Adding another layer of complexity to this already awe-inspiring picture is the concept of the multiverse. If our universe is just one of countless others that exist simultaneously in a broader multiversal framework, then its ultimate demise might be nothing more than a localized event, part of a much grander cosmic tapestry. In this scenario, the birth and death of individual universes might simply be one chapter in an ongoing, ever-expanding process. Such a perspective shifts our focus from the singular fate of our universe to the broader context of a multiverse, where the potential for other universes to emerge, evolve, and meet their own ends is an integral part of the cosmic order. The question of what happens to our universe, therefore, becomes less about the singular trajectory of one reality and more about its place within an ever-expanding multiversal narrative. The exploration of the universe's future also carries significant philosophical and existential weight. If the universe is indeed heading towards a cold, dark, and inhospitable end, what does this mean for life and intelligence within it? Advanced civilizations, if they exist, might face an extraordinary challenge, surviving in an increasingly hostile environment. As the universe cools and its energy dissipates, they would need to develop entirely new technologies, perhaps harnessing novel forms of energy or altering cosmic trajectories. The ultimate survival strategy could even involve finding ways to transcend the bounds of our own universe and journey into others. If the multiverse theory holds true, the eventual fate of our universe could be but a blip in the vast expanse of an infinite multiverse, with far-reaching implications for how life could evolve across multiple realms of existence. The contemplation of these diverse possibilities has spurred countless scientific investigations, fueled philosophical debates, and inspired imaginative explorations of the cosmos. Each potential outcome offers new insights into the nature of cosmic evolution and the ultimate fate of matter, energy, and life itself. Our understanding of the universe's future is thus an ongoing process, marked by both scientific discovery and philosophical reflection, with each breakthrough expanding the boundaries of our knowledge and imagination. The notion of a universe emerging from nothing profoundly impacts our philosophical views on existence, causality, and creation. This idea, which has captivated thinkers for millennia, forces us to reconsider what we know about the origins of reality itself. Traditionally, causality has been understood as a linear chain of events, where causes precede effects within the confines of time and space. However, if the universe itself, a vast, intricate system of matter, energy, and space-time, emerged from what we call nothing, it challenges our fundamental assumptions about how reality comes into being. In this new context, nothing might not be an empty void, but rather a quantum vacuum, teeming with potential and possibility. Quantum theory suggests that this vacuum, far from being a void, is a fertile ground for the spontaneous emergence of universes. In this probabilistic framework, quantum fluctuations may not only give rise to particles and fields, but to entire universes, each with its own set of physical laws and properties. This challenges the deterministic view of causality, replacing it with a more complex probabilistic understanding, where the origins of the universe may be driven by random fluctuations in a quantum field. This radical shift in our understanding of causality also touches on deeper existential and epistemological questions. If the universe emerged from a quantum fluctuation or a similar process, does this imply that it came into existence without a purposeful cause? This challenges traditional religious and metaphysical views, many of which posit a creator or an initial cause behind the existence of the cosmos. Instead of seeing the universe as the product of an external agent, the universe could be viewed as a spontaneous, natural occurrence, arising from the inherent potentialities of the quantum realm. Such a perspective has profound implications for our worldview. It could lead to a more secular understanding of the cosmos, one where the universe operates according to natural laws without the need for a divine or external initiator. At the same time, it raises profound philosophical questions about the nature of existence itself. What does it mean for something to exist? How do we comprehend the transition from nothingness to being? If nothingness is not an empty void, but a state brimming with quantum potential, then the very definition of nothing must be reevaluated. This opens up new avenues for philosophical inquiry, challenging our traditional concepts of potentiality and actuality, and inviting us to rethink the very fabric of reality. The idea of a universe emerging from nothing also carries profound implications for our sense of purpose in the cosmos. On one hand, it could induce a sense of existential vertigo, a feeling of insignificance in a universe that appears to have arisen spontaneously and may eventually end without inherent purpose. On the other hand, it could inspire a sense of awe and wonder at the self-organizing principles of nature, the intricate laws that govern the universe's evolution. In this view, even if the universe has no overarching purpose, it remains a magnificent and beautiful system operating according to its own natural laws. This dual perspective, one of existential anxiety and awe, encourages a deeper reflection on our place in the cosmos. The concept of a universe emerging from nothing is a powerful catalyst for interdisciplinary dialogue. It invites philosophers to engage with the latest scientific discoveries, integrating them into their metaphysical frameworks, while also encouraging scientists to grapple with the profound philosophical questions of existence, causality, and the nature of reality. This fusion of philosophy and science enriches both fields, fostering a holistic understanding of the universe and our place within it. As cosmology continues to evolve, new discoveries are shedding light on the universe's origin and its earliest moments. These revelations not only deepen our understanding of the cosmos, but also challenge our most fundamental assumptions about existence, causality, and the ultimate fate of all matter, energy, and life within it. The journey of cosmic exploration, both scientific and philosophical, is far from over, and with each new discovery, we move closer to answering some of the most profound questions humanity has ever asked. The exploration of the cosmos has reached a transformative moment, with unprecedented discoveries unlocking new chapters in the story of the universe's origin. One of the most groundbreaking developments in recent years is the work of the James Webb Space Telescope, JWST. Launched in December of 2021, the JWST is revolutionizing our understanding of the early universe, providing a level of detail that was once unimaginable. The telescope's ability to observe in the infrared spectrum allows it to capture light from galaxies that formed just a few 100 million years after the Big Bang. This unprecedented access allows astronomers to examine how these early structures evolved, shedding light on the complex processes that shaped the universe's infancy. One of the most significant revelations enabled by the JWST is the ability to peer into the very first galaxies that emerged in the universe's infancy. By capturing infrared light from distant objects whose wavelengths have been stretched by the expansion of space, the JWST helps us understand how these primordial galaxies interacted and evolved over time. These observations are giving scientists the tools to reconstruct the universe's early chapters, offering new insights into the formation of stars, black holes, and the vast cosmic structures we observe today. Another monumental discovery in cosmology comes from the cosmic microwave background radiation, CMBR. This faint afterglow, a relic of the Big Bang, holds essential information about the conditions of the universe just moments after its inception. Enhanced measurements from missions like the Planck satellite have provided the most detailed map of the CMBR ever produced. This data is invaluable for understanding the universe's initial conditions, including the distribution of matter and energy in the seconds and minutes after the Big Bang. By refining the parameters of the standard cosmological model, scientists are addressing fundamental questions about the universe's overall shape, its density, and the rate at which it is expanding. Gravitational wave astronomy has also emerged as a revolutionary tool in understanding the universe's most violent and energetic events. First directly observed in 2015 by the LIGO and Virgo collaborations, Gravitational waves are ripples in the fabric of space-time caused by cataclysmic events like the collision of black holes and neutron stars. These waves, which travel across the universe, provide a new way of observing phenomena that were previously hidden from electromagnetic telescopes. By studying these ripples, scientists can gather crucial insights into the behavior of matter and energy under extreme conditions, potentially uncovering new aspects of the early universe that remain inaccessible through traditional observations. The advent of future gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, promises to extend this research even further, enabling scientists to detect waves from earlier moments in the universe's history and probe the conditions that existed fractions of a second after the Big Bang. Despite the progress made, some of the universe's greatest mysteries remain unsolved. Dark matter and dark energy are two of the most enigmatic components of the cosmos. While dark matter has yet to be directly detected, its presence is inferred from its gravitational effects on visible matter. Ongoing experiments, such as those using highly sensitive detectors buried deep underground to shield them from cosmic radiation, aim to detect dark matter particles directly. Meanwhile, dark energy, the force responsible for the universe's accelerating expansion, continues to be a focal point of cosmological research. Observations from the Dark Energy Survey, DES, and future missions like the upcoming Euclid spacecraft aim to map the distribution of galaxies and trace the influence of dark energy over cosmic time, ultimately offering a better understanding of how this mysterious force shapes the evolution of the universe. In the realm of theoretical physics, progress continues to push the boundaries of our understanding. Theories such as string theory and quantum gravity propose new possibilities for how the universe works at its most fundamental level. Concepts like the multiverse and higher dimensional space offer tantalizing glimpses into the fabric of reality, although they remain speculative, without direct experimental or observational evidence to support them. Still, these ideas challenge the very nature of existence and inspire a deeper inquiry into the universe's origin and its true nature. Researchers are tirelessly working to unify general relativity and quantum mechanics, seeking a comprehensive theory that can describe the universe's birth and the true nature of space-time. In sum, recent advances in cosmology are dramatically transforming our understanding of the universe's birth and evolution. The James Webb Space Telescope, along with precise measurements of the cosmic microwave background radiation, gravitational wave astronomy, and the ongoing study of dark matter and dark energy, are collectively painting a more detailed and intricate picture of the cosmos in its earliest stages. These breakthroughs not only expand our knowledge of the universe's origins, but also raise new questions about the fundamental nature of reality itself. The pursuit of understanding the universe's beginning is a driving force behind the development of cutting-edge technologies, which continue to push the boundaries of exploration and allow us to peer ever deeper into the cosmos. Among the most promising of these emerging tools is the James Webb Space Telescope itself. As a marvel of engineering, the JWST is equipped with highly sensitive infrared instruments that allow it to observe galaxies and stars formed shortly after the Big Bang. Its ability to detect infrared light from these distant objects, which has been redshifted due to the expansion of the universe, is a crucial capability for studying the early cosmos. This light, though faint and stretched across vast distances, carries with it the key to understanding how the universe's first structures formed, providing astronomers with a clearer picture of the universe's infancy. In addition to space telescopes, ground-based observatories are undergoing significant advancements that will complement the work of space-based instruments. One such project is the Extremely Large Telescope, ELT, currently under construction in Chile. Upon completion, the ELT will be the largest optical and infrared telescope in the world, with a primary mirror spanning nearly 40 meters. This immense instrument will offer unprecedented resolution and sensitivity, enabling it to observe the earliest galaxies, star clusters, and other cosmic phenomena with extraordinary detail. The ELT will provide a different perspective on the universe's formative periods, complementing the findings of the JWST and other space telescopes. Gravitational wave astronomy, another rapidly advancing field, is opening new windows onto the universe's most extreme events. The LIGO and Virgo collaborations have already detected gravitational waves from black hole mergers and neutron star collisions. But the next generation of detectors promises to push the boundaries of this research. The upcoming Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory, will be capable of detecting waves with much longer wavelengths than ground-based detectors. This will allow LISA to observe the mergers of supermassive black holes and potentially even primordial gravitational waves, which could offer insights into the universe's conditions fractions of a second after the Big Bang. In the hunt for dark matter, experiments such as the Xenon 1T and its successors are employing highly sensitive detectors placed deep underground to shield them from cosmic radiation. These experiments aim to capture the rare interactions between dark matter particles and ordinary matter, hoping to uncover the nature of this elusive substance. Meanwhile, the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will map the distribution of dark matter across the universe by observing gravitational lensing effects. This will help to elucidate dark matter's role in the formation of cosmic structures and its impact on the universe's evolution. Advancements in computational technologies and simulations are also playing a critical role in our understanding of the early universe. High-performance computing allows scientists to simulate complex processes, such as cosmic inflation, the behavior of quantum fluctuations, and the formation of the first galaxies. These simulations provide valuable insights into the conditions that led to the birth of the universe and help refine the theoretical models that describe its evolution. As these technological advancements continue to unfold, our understanding of the universe's origins is expanding at an unprecedented rate. The quest to explore the cosmos to understand the universe's birth and its evolution continues to inspire new generations of scientists, engineers, and curious minds eager to uncover the mysteries of existence. Each new discovery, each new technology brings us one step closer to answering the most profound questions about the nature of reality itself. Quantum computing stands at the precipice of transforming our understanding of the cosmos. This revolutionary technology has the potential to tackle some of the most profound problems in cosmology, problems that have long been beyond the grasp of classical computers. With quantum computers, it may be possible to simulate and model aspects of the early universe, offering fresh avenues for investigating quantum gravity and other foundational aspects of physics. As we strive to uncover the secrets of the universe's inception, quantum computing could be the key to unlocking a new era in scientific discovery. Among the most remarkable achievements in international scientific collaboration is the European Space Agency's ESA involvement in the James Webb Space Telescope, JWST. While NASA operates JWST, ESA, along with the Canadian Space Agency, CSA, has played a crucial role by contributing advanced hardware, scientific instruments, and expert knowledge. This multinational partnership has greatly expanded the telescope's observational capabilities, enabling it to probe the early universe with an unprecedented level of clarity. By sharing both technological and financial resources, such collaborations make large-scale projects like JWST not only feasible, but also more comprehensive, enhancing their scientific impact. Another prime example of international cooperation in space exploration is the Planck mission, led by ESA with contributions from NASA and various European institutions. The Planck satellite provided the most detailed map to date of the cosmic microwave background radiation, CMBR, a crucial relic from the early universe that provides valuable insights into its conditions shortly after the Big Bang. This international effort brought together a diverse group of scientists and engineers from across Europe and North America, culminating in data that continues to refine our understanding of cosmological parameters and the fundamental physics governing the universe's birth. On Earth, ground-based observatories also highlight the importance of international collaboration. The Atacama Large Millimeter Submillimeter Array ALMA in Chile is a shining example of such cooperation. A partnership involving the European Southern Observatory, ESO, the National Radio Astronomy Observatory, NRAO, in the United States, and the National Astronomical Observatory of Japan, NAOJ, ALMA represents one of the most powerful millimeter and submillimeter wave telescopes in the world. It has proven indispensable in studying the cold, distant universe, including the gas clouds where the first stars and galaxies took shape. In the realm of gravitational wave astronomy, the collaboration between LIGO, Laser Interferometer Gravitational Wave Observatory in the United States, and the Virgo detector in Europe has been instrumental. Their combined observations confirmed the existence of gravitational waves, opening an entirely new frontier in astronomy. These discoveries have provided valuable insights into the extreme events and conditions of the cosmos, shedding light on the universe's most violent phenomena. With future collaborations like ESA's LISA, Laser Interferometer Space Antenna mission, which will focus on even more distant and ancient cosmic events, the study of gravitational waves promises to further deepen our understanding of the universe's origin. The Large Hadron Collider, LHC at CERN, located on the border between France and Switzerland, stands as a quintessential example of international scientific cooperation. The LHC is a massive project involving thousands of scientists and engineers from over 100 countries. The groundbreaking discoveries made here, including the identification of the Higgs boson, have profound implications for our understanding of the fundamental particles and forces that shape the early universe. This global partnership exemplifies the power of collective human effort in unraveling the mysteries of the universe at its most fundamental level. International collaboration also extends to theoretical and computational physics projects. One such initiative is the Simons Observatory in Chile, a global partnership involving institutions from the United States, the United Kingdom, and Chile, dedicated to studying the CMBR. This collaborative effort draws on diverse expertise and computational resources, allowing for more sophisticated simulations and models of the early universe, further advancing our understanding of its origins. Beyond scientific missions and experiments, global organizations play vital roles in fostering collaboration and ensuring the smooth exchange of data and knowledge. Institutions like the United Nations Office for Outer Space Affairs, UNOSA, and the International Astronomical Union, IAU, are central to promoting international cooperation in space exploration. By standardizing data protocols and encouraging the open sharing of scientific findings, these organizations help ensure that the benefits of space research are widely distributed and accessible. In conclusion, international collaborations are crucial to advancing our understanding of the universe's origins. By pooling technological resources, scientific expertise, and financial investments, these global partnerships enable the execution of ambitious projects that no single nation could undertake alone. This spirit of cooperation not only enhances scientific productivity, but also strengthens global ties, uniting humanity in the quest to explore the universe's deepest mysteries. Looking ahead, one of the most ambitious projects on the horizon is the James Webb Space Telescope, often described as the successor to the Hubble Space Telescope. Set for launch in the near future, JWST is designed to peer deeper into space and, by extension, further back in time than any telescope before it. Its advanced infrared capabilities will allow it to see through cosmic dust clouds that obscure many of the universe's earliest stars and galaxies. With this, scientists hope to observe the universe as it existed approximately 13.5 billion years ago, just after the Big Bang. Additionally, JWST's ability to study the atmospheres of exoplanets could provide valuable insights into planets that may harbor life, thereby bridging the fields of cosmology and the search for extraterrestrial intelligence. Another exciting mission from ESA, Euclid, is focused on exploring the mysterious dark universe, which includes dark matter and dark energy, collectively accounting for about 95% of the universe's total mass energy content. Using a combination of visible and near-infrared instruments, Euclid will map the three-dimensional distribution of billions of galaxies across more than a third of the sky. This massive survey will offer new insights into how dark energy influences the expansion of the universe and how dark matter holds galaxies together. Unlike previous telescopes, Euclid's wide-field survey will cover a vast area, complementing the detailed, narrow-field observations of JWST. the discoveries from Euclid could fundamentally reshape our understanding of the universe's composition and its eventual fate. Meanwhile, in recent years, new theories have emerged that challenge our conventional understanding of the universe's origins. One such theory is the concept of a quantum bounce, which offers an alternative to the traditional Big Bang model. Instead of the universe originating from an infinitely dense point that exploded outward, the quantum bounce theory posits that the universe may have gone through a previous state of contraction. Upon reaching a critical point of minimum contraction, quantum gravitational effects may have caused the universe to bounce into its current state of expansion. Rooted in the framework of loop quantum gravity, this theory suggests that the universe could have undergone endless cycles of expansion and contraction. If proven correct, this would imply that the universe is far older than the currently accepted age of 13. 8 billion years, and our understanding of the universe's life cycle would need to be drastically revised. Another provocative idea gaining traction is the multiverse hypothesis, which posits that our universe is but one of many, perhaps an infinite number that exists simultaneously. Stemming from string theory and the inflationary model of cosmology, this hypothesis suggests that the rapid expansion of space immediately after the Big Bang could have led to the creation of bubble universes, each with its own distinct physical laws and constants. These parallel universes may exist in dimensions beyond our observable reality, making them nearly impossible to detect with current technology. If this hypothesis proves accurate, it could have profound implications for our understanding of the cosmos and our place within it. However, should definitive evidence for the multiverse theory emerge, it would spark a revolution in cosmology, radically reshaping our understanding of the universe and its origins. The implications would be profound, suggesting that the reality we observe might be but a small fragment of a vastly larger, more intricate existence. Our universe's origin, rather than being a solitary event, would become one chapter in a much grander cosmic narrative, perhaps an infinite, ongoing epic. This new perspective would not only broaden the scope of cosmology, but could also challenge fundamental concepts of existence itself. Cosmologists, whose views on the universe's origin are as diverse as the theories they propose, continue to wrestle with these grand mysteries. Despite ongoing debates, many scientists still adhere to the Big Bang theory. This model suggests that approximately 13.8 billion years ago, the universe began from an incredibly hot and dense singularity, a point of infinite density. From this explosive origin, the universe expanded, leading to the cosmos we observe today. This theory offers a robust framework to explain key phenomena, such as the universe's observable expansion, the cosmic microwave background radiation, and the distribution of elements across space. Yet, even the staunchest supporters of the Big Bang theory acknowledge its limitations, particularly when it comes to answering questions about what occurred before the Big Bang or what may have caused it. Some leading figures in cosmology, including Stephen Hawking and Roger Penrose, have speculated that time itself may have begun with the Big Bang. In this view, asking what came before may be an inherently meaningless question, because according to our current understanding of physics, time itself would not have existed prior to this moment. Other cosmologists, such as Sir Martin Rees and Alan Guth, have sought to expand the boundaries of the Big Bang model by proposing alternative or supplementary theories. Alan Guth, in particular, is a prominent advocate of the inflationary universe theory, which postulates that the universe underwent a brief but dramatic period of exponential expansion mere fractions of a second after the Big Bang. This inflationary phase could help explain many of the large-scale uniformities and structures we see in the cosmos, including the even distribution of galaxies and the smoothness of the universe on vast scales. Meanwhile, Sir Martin Rees has suggested a radically different approach, contemplating the possibility of a multiverse, a collection of universes, each potentially governed by its own unique set of physical laws. In this view, our universe might be just one of countless others, each with its own distinctive properties and history. Renowned cosmologist Lisa Randall has further expanded the conversation with her groundbreaking work on extra dimensions. She has proposed that our universe could have more than the familiar 3 spatial dimensions and 1 time dimension. If true, this idea would dramatically alter our conception of the cosmos and our place within it, opening up new avenues for exploration and discovery. While the Big Bang Theory remains a cornerstone of modern cosmology, these alternative theories suggest that our understanding of the universe's ultimate origin may still be in its infancy. Leading cosmologists are pushing the boundaries of existing models and exploring new frameworks that could revolutionize our knowledge. Quantum physics has also introduced some provocative perspectives on the origin of the universe. One of the central ideas in this discourse is the concept of quantum fluctuations, temporary changes in energy that occur spontaneously, even in what we consider empty space. According to the principles of quantum mechanics, these fluctuations can lead to the creation of particles and antiparticles, essentially giving birth to matter from a state that initially has no material substance. Physicist Lawrence Krauss has been particularly vocal in popularizing the idea that a universe could emerge from nothing. In his view, quantum mechanics permits the spontaneous generation of a universe through fluctuations in the vacuum of space. Krauss argues that the energy inherent in these fluctuations could serve as the seed for a new universe, making the creation of the cosmos from nothing a physically plausible scenario. Further expanding on this notion, some quantum physicists have linked the idea of the multiverse to the inflationary model. According to this framework, our universe might simply be one bubble in a much larger multiverse, with each bubble emerging from quantum fluctuations in different regions of space. In this vision, the traditional concept of a singular, well-defined initial condition, as posited by the Big Bang Theory, is replaced by a dynamic, ever-changing landscape where regions of space continually fluctuate, producing energy and expanding into new universes. This theory not only aligns with the principles of quantum field theory, but also reveals an elegant and intricate process by which new universes could arise from the fundamental properties of space itself. As quantum physicists push the boundaries of our understanding, they are transforming how we think about the origins of the universe. By exploring ideas that challenge traditional cosmology, they are opening new avenues for scientific inquiry and forcing us to rethink what we know about existence. Astronomers, too, have been pivotal in expanding our knowledge of the early universe, offering crucial insights into its formation and early development. One of the most groundbreaking discoveries came in 1965 with the detection of the cosmic microwave background radiation, often described as the afterglow of the Big Bang. This faint radiation, which permeates the entire universe, serves as a snapshot of the cosmos when it was just 380,000 years old, providing a unique window into its primordial state. By studying the slight temperature fluctuations in this radiation, astronomers have been able to infer the distribution of matter and energy in the young universe, offering invaluable clues about its structure and composition during its earliest stages. These studies have provided strong evidence for the Big Bang Theory, as well as for the subsequent period of inflation, confirming many of the fundamental tenets of modern cosmology. Another area of significant research in cosmology focuses on the formation and evolution of the first galaxies and stars, a period often referred to as cosmic dawn. Using powerful telescopes like the Hubble Space Telescope and, in the near future, the James Webb Space Telescope, astronomers aim to observe these ancient celestial bodies, which formed between a few hundred million and 1 billion years after the Big Bang. These early structures played a pivotal role in shaping the universe, triggering a series of events that made the cosmos transparent to ultraviolet light and marking the end of the so-called cosmic dark ages. By examining the light emitted by these distant galaxies and stars, astronomers are able to piece together vital information about the physical conditions, chemical compositions, and processes that governed the early universe. Such observations not only deepen our understanding of the evolution of the cosmos, but also have profound implications for our comprehension of how the galaxies and larger structures we observe today came to be. As the field of cosmology continues to evolve, it remains an exciting and dynamic area of scientific inquiry. Whether through the lens of quantum physics, the study of the cosmic microwave background, or the quest to uncover the origins of the first galaxies, researchers are inching ever closer to unraveling the deepest mysteries of the universe. The more we learn, the more we realize how much remains to be discovered, and the further we move from the boundaries of our current understanding. The universe, it seems, holds endless secrets, waiting to be revealed. Philosophers have long approached the concept of the universe emerging from nothing with a mixture of fascination and skepticism. The idea, rich with metaphysical and existential implications, invites contemplation on the nature of existence itself. Traditionally, the philosophical exploration of nothingness does not treat it simply as an empty void or a vacuum, but as a profound state completely devoid of properties, entities, or even potentiality. In this framework, the concept of the universe arising from absolute nothingness directly challenges one of the most foundational principles of philosophy, the principle of sufficient reason. This principle asserts that everything must have a cause, an explanation, or a reason for its existence. One of the most prominent figures to grapple with this dilemma was the philosopher Martin Heidegger. He famously asked, "Why is there something rather than nothing?" This deceptively simple question encapsulates the deep and perplexing nature of the problem. How can a universe, with all its complexity, arise without an underlying cause or pre-existing conditions? The question has perplexed philosophers for centuries, leading them to probe not only the origins of the universe, but also the very nature of being and non-being. In contemporary philosophy, the conversation has broadened to include scientific insights, particularly from the fields of quantum mechanics and cosmology. The philosopher Alexander Vilenkin, for instance, has aligned his ideas with some interpretations of quantum physics to propose that the universe could have emerged from a quantum vacuum. This vacuum is not an empty space, but a kind of nothingness that contains latent potential, governed by the laws of physics. However, this brings a new layer of philosophical inquiry. If this vacuum has inherent properties, such as the potential for the formation of matter and energy, can it truly be considered nothing? Philosophers like David Albert have raised critiques of such scientific models, arguing that a quantum vacuum is far from the absolute nothingness that classical metaphysics contemplates. In his view, these scientific models point to a different kind of existence, one with its own complexities and subtle laws, not an absolute void. The dialogue between philosophy and science, thus, enriches our understanding by pushing the boundaries of how we define existence and non-existence. Philosophers and scientists in tandem question not just the origins of the universe, but also the very frameworks through which we interpret those origins. These questions challenge us to reconsider fundamental concepts such as causality, existence, and the nature of reality itself. Whether philosophical in nature or rooted in scientific inquiry, the ongoing discussion about the universe's emergence from nothing reveals the tension and synergy between the two fields. The scientific approach, with its focus on physical laws and empirical evidence, often contrasts with the metaphysical concerns of philosophers who look beyond physical causality. Nevertheless, both perspectives offer essential insights into understanding the profound idea of the universe's origin, shedding light on the profound intersections between human reason, scientific discovery, and metaphysical reflection. In addition to philosophers, theologians have pondered the origins of the universe, often framing their discussions within the context of divine creation. In many religious traditions, the idea that the universe had a beginning is tightly intertwined with the concept of a creator, a being or force responsible for bringing all things into existence. For instance, in the Judeo-Christian tradition, the book of Genesis speaks of God creating the heavens and the earth from a formless void, signifying a deliberate and purposeful act of creation. From this theistic perspective, the beginning of the universe is not a random event, but a meaningful act imbued with intentionality and purpose. Similarly, Islamic theology holds that Allah created the universe through a divine command, emphasizing that the orderly nature of the cosmos reflects divine will. The Quran speaks of Allah's creative power as central to the existence of the universe, with all of creation existing as a reflection of the divine. In Hindu cosmology, the creation of the universe is understood as part of an eternal cycle of birth, destruction, and rebirth. Here, Brahma, the creator god, brings forth the universe, which is sustained by Vishnu and ultimately destroyed by Shiva, only to be created anew in an endless cycle. This view emphasizes an ongoing, cyclical process rather than a singular, linear beginning. In modern theology, some theologians seek to reconcile traditional religious views with contemporary scientific models, particularly the Big Bang theory. They may see the Big Bang not as a challenge to the idea of divine creation, but as the method through which a divine being brought the universe into existence. Figures like Pope John Paul II have expressed the view that the Big Bang theory does not conflict with the notion of divine creation, right, but rather describes the process by which God's creative act unfolded. This interpretation allows for a blending of scientific insight and theological doctrine, offering a vision of the universe's origin that honors both spiritual and scientific understandings. Other theologians take a more abstract approach, contemplating the metaphysical implications of a universe with a definite beginning. They reflect on profound questions such as, why is there something rather than nothing? What does this say about the nature of existence? And what does it imply for human life and the divine? These theological explorations often lead to a deep sense of awe and wonder, inviting reflection on the mystery of existence that transcends mere physical explanations. The theological perspective adds a rich dimension to the conversation on the universe's origins. By blending scriptural interpretations, doctrinal beliefs, and philosophical reflection, theologians contribute significantly to our understanding of the cosmos. Their perspectives provide an additional layer of meaning to the universe's beginning, imbuing it with purpose and significance. These theological reflections intersect with, but are distinct from, scientific and philosophical frameworks, offering a multifaceted approach to one of humanity's most profound questions. Visually representing the Big Bang and the early universe presents a unique challenge for both artists and scientists. This task involves translating complex scientific concepts into clear, accessible images that can help the general public understand the universe's origins. One of the most iconic depictions of the Big Bang is the image of a vast explosion, though this is a simplification of the actual event. In reality, the Big Bang was not an explosion in space. Rather, it was the rapid expansion of space itself. Artists often depict this as a brilliant flash of light emanating from a singular point, with matter and energy spreading outward in all directions. To further illustrate the early universe, scientists rely on detailed, color-coded maps created from data collected by satellites, like the Cosmic Background Explorer, COBE, and the Wilkinson Microwave Anisotropy Probe, WMAP. These maps show the cosmic microwave background radiation, the afterglow of the Big Bang. The radiation appears as a speckled multicolored pattern with slight variations in temperature that correspond to density fluctuations in the early universe. These fluctuations eventually led to the formation of galaxies and large-scale cosmic structures. By translating minute temperature differences into visual cues, these maps offer a snapshot of the universe when it was just 380,000 years old. They show us the seeds of cosmic structure, which would later develop into the galaxies, stars, and planets we see today. Alongside these maps, timelines of the universe's evolution are often used to show the major milestones from the Big Bang to the present. These timelines divide the universe's history into key phases, such as inflation, the formation of the first atoms, the cosmic dark ages, and the era of reionization. Such visualizations provide a narrative of the universe's complex and fascinating evolution, helping us contextualize and understand its extraordinary journey from its fiery beginnings to the present day. In the vast expanse of space, where the mysteries of the universe unfold at unimaginable scales, the role of three-dimensional simulations and animations has proven to be invaluable. These visualizations offer a window into the unseen and often incomprehensible processes that shaped the cosmos. Through advanced computer-generated models, we are able to observe how primordial fluctuations born from the Big Bang slowly grew into the vast structures we now recognize as galaxy clusters and superclusters, all under the profound influence of gravity. By simulating the intricate dance of cosmic forces, these visualizations bring a dynamic and immersive quality to the cosmos, helping us to not only understand but also feel the enormity and beauty of the universe. As viewers, we are no longer passive observers. The animations pull us into the experience. providing a unique opportunity to interact with concepts that were once purely abstract. They bridge the divide between artistic creativity and scientific rigor, blending the two into an experience that is as awe-inspiring as it is informative. What was once confined to textbooks or complex equations is now tangible, a vivid depiction of the forces and phenomena that govern our universe. These visual representations make the Big Bang, the birth of galaxies, and the early moments of the universe more comprehensible to the public, while also evoking a sense of wonder and curiosity about the world beyond our own. One of the standout features of these animations is their ability to make complex cosmological concepts more accessible. Animation acts as a powerful tool to explain ideas that are not only difficult to grasp through traditional text-based descriptions, but also often counterintuitive to our daily experiences. For example, the concept of cosmic inflation, where the universe expanded exponentially in a fraction of a second after the Big Bang, can seem nearly impossible to visualize. But with the help of animation, the rapid expansion of a tiny, dense point into the vast universe we see today becomes strikingly clear. Viewers can see in real time the immense speed and scale of this expansion, something words alone could never fully convey. Animations also excel at representing the dynamic nature of astronomical phenomena. For instance, they can condense billions of years of galactic evolution into a few minutes, showcasing the gradual collapse of density fluctuations in the early universe, which eventually gave rise to stars, galaxies, and all the structures that populate our cosmic landscape. Such visualizations allow us to witness cosmic evolution in ways that static images or theoretical models could never achieve, making the unfolding of the universe feel immediate and real. This ability to simulate processes that happen on scales beyond human experience is one of animation's greatest strengths. Take, for example, the phenomena of black hole mergers or gravitational lensing, where the bending of light by gravity creates spectacular effects. Through high-fidelity animations, these complex theories come to life, offering us clear and impactful demonstrations of how these processes work. Viewers can virtually witness the intense gravitational interactions of massive objects, which are otherwise invisible to our eyes, thanks to the power of animation. Moreover, animation plays a crucial role in visualizing concepts that, by their very nature, are abstract or far beyond the reach of current observational technology. Consider the multiverse theory, which posits the existence of multiple universes with varying physical laws. While we can never observe these other universes, animation allows us to creatively imagine how these regions of space might behave, providing a more tangible understanding of this speculative concept. Similarly, animations can delve into the quantum realm, illustrating how minute fluctuations at the subatomic level could potentially give rise to entire new universes, helping to bridge the often daunting gap between quantum mechanics and cosmology. From an educational standpoint, animations serve as invaluable teaching tools. They break down complex scientific concepts into digestible, step-by-step sequences, often enhanced by narration that helps reinforce learning. Reputable scientific organizations such as NASA and the European Space Agency, ESA, as well as educational platforms like Khan Academy, frequently use animations to explain everything from the life cycle of stars to the vast expansion of the universe. By transforming dense scientific data and theories into captivating visual narratives, animations not only enhance comprehension, but also spark interest and curiosity in viewers, making the wonders of the universe more accessible to all. At the intersection of science and art, animation plays an indispensable role in cosmology. It serves as a bridge, linking intricate scientific ideas with the general public's understanding and fostering a deeper appreciation for the cosmos. In this collaborative process, scientists and artists work together to craft compelling, accurate representations of the universe's origins. The process begins with scientists providing the foundational data, mathematical models, and theoretical frameworks that underpin our understanding of the cosmos. These raw materials, data from telescopes like the Hubble Space Telescope, cosmic microwave background observations, and simulations of the Big Bang, form the basis for the artistic work to come. Artists then use their creative skills to transform these abstract concepts into visually engaging simulations. This process requires close collaboration between scientists and artists to ensure the scientific accuracy of the visuals. Artists might, for instance, work on generating high-resolution maps of the cosmic microwave background radiation, ensuring that variations in temperature and density are accurately depicted. Advanced animation software allows them to create simulations of key events in the early universe, from the Big Bang itself to the rapid inflationary phase that followed. These animations are typically refined through iterative feedback from scientists, ensuring that each stage of the process brings the visuals closer to scientific accuracy and clarity. One of the best examples of this collaboration is the work done for planetarium shows or educational documentaries. In such settings, scientists may describe the early conditions of the universe, while artists bring those descriptions to life with immersive 360-degree animations. These animations transport viewers to the moments right after the Big Bang, offering a front-row seat to the birth of the cosmos. They might feature dramatic depictions of primordial gas coalescing into the first stars, the formation of galaxies, and the vast, ever-expanding structure of the universe, all while remaining true to the scientific narrative. Through these powerful animations, we not only understand the cosmos better, but are also left in awe of its scale, complexity, and beauty. The synergy between scientific insight and artistic expression creates a lasting impression, helping us to grasp the most profound mysteries of the universe. In this way, animation doesn't just help us learn about the cosmos, it immerses us in its very fabric, inviting us to explore its deepest secrets. Interdisciplinary efforts have the potential to transform our perception of the cosmos in profound and unexpected ways. When artists, scientists, and cutting-edge technologies converge, they create tools and experiences that allow us to engage with the universe in entirely new forms. One of the most exciting aspects of these collaborations is the development of interactive and immersive resources that bring the abstract concepts of cosmology into tangible experiences for the public. Virtual reality, VR, headsets, for example, offer users the chance to travel back in time and experience the birth of the universe firsthand. Imagine standing on the threshold of creation, witnessing the unfolding of the cosmos at its origin. VR experiences can offer something that static images and traditional media simply cannot: a dynamic, three-dimensional view of space and time. This allows individuals to grasp the vastness and scale of the universe in ways that traditional media cannot capture. By blending the analytical precision of scientific data with the evocative power of visual art, these collaborations transcend the boundaries of traditional storytelling. The result is not only an enhanced understanding of the universe's beginnings, but also an accessible and engaging means of communicating that story to a broad audience. For instance, a detailed, color-coded visualization of the cosmic microwave background, CMB, radiation can convey the universe's state just 380,000 years after the Big Bang. These maps reveal the subtle temperature variations across the universe, which correspond to density fluctuations in the early cosmos. Over billions of years, these fluctuations form the galaxies and larger cosmic structures that populate the universe today. The colors on the map, shades of blues, reds, and greens, offer a glimpse into the universe's primordial conditions, providing a sensory experience of its complex, multifaceted nature. Another compelling visualization comes from depictions of cosmic inflation, the rapid, exponential expansion of space that occurred a fraction of a second after the Big Bang. Through animations, this concept is transformed from an abstract scientific idea into something we can begin to understand. Expanding grids or ballooning spheres are often used to convey the mind-boggling speed and scale of inflation, making it easier to grasp just how rapidly the universe expanded from an infinitesimally small, incredibly dense point to the vast cosmos we see today. These animations are powerful tools that transform abstract concepts into visual, tangible experiences. Perhaps even more captivating are simulations of the formation of the first stars and galaxies, often referred to as the cosmic dawn. These visualizations illustrate how gravitational forces caused gas and dark matter to collapse into the first luminous objects. As viewers watch the transformation, they witness the early universe, initially homogeneous, gradually filling with clusters of galaxies, dark matter filaments, and other complex structures. These simulations encapsulate the grand scale of cosmic evolution, condensing billions of years into a few minutes of visual exploration. The rapid transitions from chaos to structure provide a mesmerizing overview of the forces that have shaped the universe over time. On a grander scale, simulations like the Millennium simulation provide a striking visualization of how galaxies are distributed throughout the cosmos. These highly detailed simulations, run on powerful supercomputers, combine observational data with theoretical models to recreate the vast cosmic web. Galaxies are shown in vast clusters, connected by enormous, empty voids, capturing the complex and interconnected nature of the universe on the largest scales. These visualizations present a cosmic landscape teeming with life and activity, while also revealing the emptiness and vastness between galactic structures. Interactive tools such as VR experiences and planetarium shows take these visualizations to an even higher level of engagement. With VR, users can soar through the early universe, witnessing the formation of the first stars or traversing the cosmic web of galaxies. These experiences go beyond the visual. They immerse users in a sensory, three-dimensional understanding of the universe. Planetarium shows, with their immersive 360-degree visuals and carefully crafted narration, take this a step further, combining the wonder of cosmic discovery with a deeply educational experience. They invite viewers to experience the universe in a way that is both informative and awe-inspiring, transforming complex scientific concepts into something relatable and accessible to all. What makes these visualizations so impactful is not just their ability to communicate complex data, but also the way they evoke a sense of wonder. By making the universe's origins visually accessible, these collaborative efforts inspire curiosity and invite us to explore our place within the vast expanse of space. The narratives of the cosmos, from the birth of galaxies to the emergence of life on Earth, form a compelling story that bridges the gap between the scientific community and the public. These visualizations don't just illuminate scientific concepts, they make them compelling and human, inspiring a deeper connection to the universe itself. The origin of the universe has long captured the imagination of thinkers, scientists, and dreamers alike. The implications of understanding how everything, from the tiniest particle to the largest galaxy, has a shared history stretching back billions of years is both humbling and awe-inspiring. This realization is at the heart of the quest to understand cosmology, to comprehend not only the mechanisms behind the universe's birth, but also our place in this immense, ever-evolving story. For me, this fascination began with the mind-boggling idea that the universe we see today began with an event, the Big Bang, that occurred approximately 13.8 billion years ago. This moment, the beginning of space and time, set in motion a series of events that continue to puzzle and inspire us. What struck me most as I delved deeper into cosmology was the realization that each new discovery is but a small piece of a much larger cosmic puzzle. The cosmic microwave background, CMB radiation for instance, offers a snapshot of the universe when it was just 380,000 years old, at a time when temperatures were so high that atoms couldn't even form. The faint glow of the CMB, detected as microwave radiation, is a whisper from the infant universe, a signal from a time when the cosmos was in its earliest, most chaotic moments. This subtle glow, echoing through space and time, carries with it secrets about the universe's birth and its subsequent evolution. Over time, my understanding of the universe's origins has evolved alongside the development of cosmology itself. In the beginning, the idea of the Big Bang was almost mystical, a vague and abstract event. However, as I learned more, this initial mystery began to crystallize through the lens of scientific discovery. The breakthrough came with the discovery of the cosmic microwave background radiation, which served as definitive evidence that the Big Bang was not just a theoretical concept, but a cornerstone of our understanding of cosmic history. In parallel with these discoveries, the advent of powerful observational tools, such as the Hubble Space Telescope and the James Webb Space Telescope, has allowed us to peer deeper into the universe than ever before. These telescopes have captured light from galaxies that formed only a few 100 million years after the Big Bang, helping us understand how the universe evolved in its earliest stages. The precision of these tools has allowed us to measure the rate of expansion of the universe, the existence of dark energy, and even the cosmic inflation that occurred in the first moments of the universe's existence. Each of these discoveries has refined our understanding of the universe, transforming the Big Bang from a simple explosive event into a complex dance of physics, space, and time. The universe, as we now understand it, is not a static entity, but a dynamic, ever-changing entity that has evolved over billions of years. By studying the origins of the cosmos, we not only learn about its history, but also gain insights into our own existence and our place within it. My hope is that viewers come away from this exploration with a deeper sense of awe and wonder, recognizing the intricate beauty of the cosmos. The universe, with its vastness and complexity, can often seem incomprehensible. Yet, through engaging with it, both intellectually and emotionally, we can begin to appreciate its profound mysteries. The universe is not merely a backdrop to our lives. It is a living, breathing entity that has evolved alongside us. Understanding the origins of the universe challenges us to rethink our place within it and to consider the broader implications of our existence. This journey into the cosmos is a deeply transformative experience, one that can profoundly shift our perspective on life, the universe, and everything within it. As we embark on this journey through the cosmos, I hope this documentary sparks a sense of wonder and ignites a deep curiosity about the vast realm of science and exploration. The collaborative efforts of scientists from diverse disciplines form the backbone of this quest to understand the universe. By exploring the scientific methods they employ to uncover its mysteries, viewers can come to appreciate the essential value of inquiry, skepticism, and evidence-based reasoning. The story of the universe, stretching from the moment of the Big Bang to the present day, is not just one of scientific discovery. It is a narrative of human resilience, collective intelligence, and the relentless pursuit of knowledge. It is a story full of challenges, breakthroughs, and new horizons that scientists continue to push forward. By telling this story, my hope is to do more than just inform. I aim to inspire viewers to explore their own questions, seek answers, and maybe even contribute their own insights to the never-ending quest to understand the cosmos. The universe's story is far from over. It is still being written, and each new discovery adds to the ongoing chronicle of existence. This journey of exploration is open to all, and there is always room for new perspectives, new questions, and new minds. The universe's mysteries are vast, but there is a space for everyone in its exploration. Studying the origins of the universe has profoundly altered my view of humanity's place in the grand expanse of the cosmos. To grasp that every atom, every particle that makes up our bodies, once formed in the cores of ancient stars, is to realize a deeply woven connection to everything around us. We are not isolated beings, detached from the world, but rather an intricate part of an ever-evolving cosmic fabric that stretches across time and space, spanning billions of years. This realization draws a powerful link between our existence and the celestial forces that have shaped the universe, from the birth of the first particles to the creation of vast galaxies. The very atoms in our bodies were forged in the fiery hearts of dying stars. In recognizing this, we can appreciate that our lives are not separate from the universe, but are intimately tied to its ongoing story. This cosmic perspective sheds light on both the fragility and the uniqueness of life on Earth. The enormity of the universe, coupled with its mind-boggling complexity, makes the existence of life on our planet seem all the more extraordinary. Earth, with its precise and rare conditions, has managed to nurture life, a fact that demands our deep respect and stewardship. It is a fragile balance that has taken billions of years to achieve, and understanding this prompts a powerful reminder. We must protect and care for this planet, not only for our own sake, but for the generations to come. This realization also serves as a call to arms for scientific inquiry and collaboration. The pursuit of knowledge is not just an academic endeavor. It is a moral responsibility we share as caretakers of this planet and as participants in the universe's unfolding story. The study of the universe's origins does not merely expand our intellectual horizons, but also enriches our philosophical and ethical understanding of our place in the cosmos. It challenges us to embrace the responsibility we have towards each other and the planet we share. The next phase of my journey to understand the universe's origins will take me deeper into both theoretical explorations and hands-on observations. On the theoretical side, it is crucial to stay abreast of breakthroughs in fields like particle physics and quantum mechanics. These disciplines hold the keys to unlocking the mysteries of the universe's earliest moments, potentially shedding light on cosmic inflation and the very nature of the Big Bang singularity itself. To stay informed, I will engage with the latest research papers, attend scientific conferences, and immerse myself in discussions that push the boundaries of current understanding. At the same time, advancements in astronomical observations are just as essential in piecing together this story. The James Webb Space Telescope, with its unparalleled infrared capabilities, promises to uncover some of the earliest galaxies, and perhaps even the first stars, formed after the Big Bang. These ancient objects, some of which have been hidden from view for billions of years, offer vital clues that will help us reconstruct the universe's early history. By studying these distant relics, we can move closer to a complete narrative of the universe's infancy. Collaboration is key. By working with astronomers, cosmologists, and even participating in citizen science projects, I can gain firsthand access to groundbreaking discoveries. Projects like the Large Synoptic Survey Telescope, LSST, are poised to revolutionize our understanding of dark matter and dark energy, two of the most mysterious and fundamental components of the universe. These scientific collaborations, combined with the latest technological advancements, will lead to breakthroughs that could change everything we know about the cosmos. By combining theoretical research with practical observations, and by maintaining a curious and open-minded approach, I hope to contribute to the ever-growing body of cosmic knowledge. This journey is not only about finding answers, but also about the questions we uncover along the way. Each step we take brings us closer to unraveling the profound mysteries of the universe, but there is always more to explore, always more to discover. This is a journey that will never truly end, and each discovery will lead to new questions, new pathways of exploration. In this sense, the story of the universe is not just something to be understood, it's something we are all part of, something that continues to evolve with every question asked and every answer found.